Cek satu, cek satu, tes satu.
Ah, apa? Bebas, 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 Pak. Bukan. Kamera.
Bagus ya.
Halo. Halo. Selamat pagi.
Karena sudah benar.
Kaset dong.
Texan.
Ada.
Masuk
Masuk,
ya.
masuk. Mute dulu aja deh. Jalan.
Negeri Pontianak, jurusan Teknik Sipil. Jurusan Teknik Sipil Politeknik Negeri Pontianak memiliki 3 program studi, yakni program studi D3 Teknik Sipil, program studi Sarjana Terapan Perencanaan Perumahan dan Pemukiman, serta program studi Sarjana Terapan Teknik Rekayasa Konstruksi Jalan dan Jembatan. Program studi Sarjana Terapan Teknik Rekayasa Konstruksi Jalan dan Jembatan merupakan program studi baru di jurusan Teknik Sipil Pontianak yang lahir di tahun 2023. Fasilitas program studi yang didapatkan oleh mahasiswa diantaranya adalah workshop kerja kayu, workshop kerja beton, workshop kerja drainase, workshop kerja baja, workshop kerja batu, dan workshop kerja acuan perancah. Selain itu juga terdapat fasilitas laboratorium yang terdiri dari laboratorium aspal, laboratorium beton, laboratorium tanah, dan laboratorium hidrolika. Ruang kelas yang memadai, ruang jurusan, ruang program studi, dan ruang kerja dosen. Semua fasilitas yang ada telah memenuhi kualifikasi dan standar yang berlaku. Semua program studi dapat ditempuh dengan jalur SNMPTN, SMBPTN, dan jalur seleksi mandiri.
Assalamualaikum warahmatullahi wabarakatuh. Jurusan Teknik Sipil adalah salah satu jurusan yang berada di lingkungan Politeknik Negeri Pontianak. Jurusan Teknik Sipil memiliki 3 program studi, di antaranya program studi D3 Teknik Sipil, program studi Sarjana Terapan Perencanaan Perumahan dan Pemukiman, serta yang terbaru tahun ini adalah program studi Sarjana Terapan Teknologi Rekayasa Konstruksi Jalan dan Jembatan. Jurusan Teknik Sipil juga dilengkapi ruang laboratorium dan bengkel, di antaranya laboratorium tanah, laboratorium aspal, laboratorium beton, laboratorium hidrolika, dan laboratorium survei. Sedangkan bengkel dilengkapi dengan kerja baja, kerja kayu, dan kerja beton. Jurusan Teknik Sipil juga melakukan berbagai kerjasama di bidang teknik sipil. Di antaranya pelatihan dengan Dinas PUPR, baik dinas kota maupun provinsi, dan berbagai pengujian di laboratorium dengan berbagai industri lainnya, di antaranya laboratorium tanah, laboratorium aspal, dan laboratorium beton.
Mahasiswa Teknik Sipil Politeknik Negeri Pontianak juga aktif dalam kegiatan perlombaan, baik perlombaan regional maupun nasional. Jurusan Teknik Sipil juga aktif dalam kegiatan kerjasama bersama industri dan PUPR. Diharapkan mahasiswa jurusan Teknik Sipil Politeknik Negeri Pontianak dapat membentuk generasi Indonesia seutuhnya yang memiliki dedikasi, integritas, dan komitmen yang tinggi dalam mengabdikan dirinya secara profesional untuk menunjang pembangunan nasional. Selamat datang di Politeknik Negeri Pontianak, jurusan Teknik Sipil. Jurusan Teknik Sipil Politeknik Negeri Pontianak memiliki 3 program studi, yakni program studi D3 Teknik Sipil, program studi Sarjana Terapan Perencanaan Perumahan dan Pemukiman, serta program studi Sarjana Terapan Teknik Rekayasa Konstruksi Jalan dan Jembatan. Program studi Sarjana Terapan Teknik Rekayasa Konstruksi Jalan dan Jembatan merupakan
It is my great pleasure to introduce the next.
Dan juga pada kesempatan ini hadir Ketua PPMPP Pak Wendy, kemudian ada Kepala UPA ya. Di sini ada Pak Estar, Pak Boy ya tadi Pak Boy. Baik, ladies and gentlemen, distinguished guests, esteemed colleagues and friends, good morning and welcome to the international webinar on civil engineering research held by the Civil Engineering Department of Politeknik State, Pontianak State Polytechnic. It is an honor and a privilege to be here today as we come together to exchange ideas, share our latest research, and contribute to the ongoing advancement of advanced technology in sustainable civil engineering infrastructure that shape our built environment and support the sustainable development. Bapak Ibu yang saya hormati, besar harapan kita bahwa seminar ini akan menambah wawasan kita tentang teknologi di bidang teknik sipil, sehingga menambah wawasan kita dalam proses PBM khususnya, Dan tentunya harapannya adalah bisa diimplementasikan dalam kehidupan sehari-hari. Mungkin itu makna sustainable-nya tadi. This webinar serve a platform to showcase cutting-edge research, promote cross-border collaboration, and foster a global dialogue on the pressing issues and emerging trends with civil engineering. Your collaborative knowledge, experience, and expertise will contribute to advancing our understanding of critical areas such as structural engineering, material science, and construction technology. As we share our finding, I would like to take this opportunity to express my sincere gratitude to all of you for your participation and contributing to this international webinar. I extend a special thanks. I extend to a special thank you to our presenters. I encourage all of us to remain open-minded, to change each other and webinar internasional dengan judul Advanced Technology in Sustainable Civil Engineering Infrastructure, saya nyatakan dibuka. I wish you all a productive, inspiring, and successful webinar. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Mr. Irawan Suharto. Ladies and gentlemen, to ensure the smooth progress of our event, let us begin with a prayer. To Mr. Didi M. Nur Haris, LC, MSH, PhD, please lead the prayer.
Assalamualaikum warahmatullahi wabarakatuh. Good morning and peace be upon us all. Let us begin our event by opening our heart and mind, seeking blessing from Allah Subhanahu wa Ta'ala, so that we may receive grace and smooth proceeding from beginning to end. Please allow me to lead the prayer. A'udzu billahi minasyaitonir rajim. Bismillahirrahmanirrahim. Alhamdulillahi rabbil alamin. Wassalatu wassalamu ala asyrafil anbiya'i wal mursalin. Sayyidina wa nabiyyina Muhammadin wa ala alihi wa sahbihi wa sallim ajma'in. Ya Allah, Ya Rahman, the most gracious as merciful. All praise and gratitude are always offered to you for the grace and blessing that you have bestowed on us, allowing us to gather here from this event. Therefore, Ya Allah, Ya Rahman, Ya Kareem, make this event the event that you are pleased with, which will bring blessing, mercy, and guidance to us. Ya Allah, Ya Alim, the source of knowledge, make this event is an opener of your knowledge, is a motivation for us to innovate further. Therefore, Ya Allah, grant us health, strength, intelligence, ease, sincerity, and wisdom in all our activity. Ya Allah, Ya Jami', the gathering, unite all our potential, bring together all our strengths, unite our heart to work together toward creating the prosperous and blessed nation. Baldatun tayyibatun wa rabbun ghafur. Keep us away from pride and jealousy. Keep us away from division that will destroy our future. Cleanse us all from all seed of hostility. Guide us always under your guidance. Ya Allah, the forgiver, the most forgiving. You are the most forgiving of all sins. Forgive our sins, the sin of our parents, the sin of our leaders, the sin of our warriors, and the sin of our predecessor. Place us and all of them under the protection of your mercy and forgiveness. Ya Allah, Ya Mujib, the responders of to all prayers, answer our prayers and fulfill our hopes. Rabbana atina min ladunka rahmatan wa hayyi' lana min amrina rashada. Allahumma inna nas'aluka ilman nafi'a wa rizqan tayyiba wa amalan mutaqabbala. Rabbana zalamna anfusana wa illam taghfir lana wa tarhamna lanakunanna minal khasirin. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina adzaban nar. Wa sallallahu ala nabiyyina Muhammad wa ala alihi wa sahbihi wa sallam. Subhanaka rabbika rabbil izzati amma yasifun wa salamun alal mursalin walhamdulillahi rabbil alamin. Assalamualaikum warahmatullahi wabarakatuh.
Warahmatullahi wabarakatuh. Thank you very much, Mr. Didi M. Nur Haris. Seems that we're going to go directly to our discussions. Ladies and gentlemen, our distinguished guests and honored guests today, thank you very much. All right. Please, we're going to have a photo taken together with the audience in here. Excuse me, maybe we could just line in here in the front. The head of the departments, to Mr. Chandra. Ibu. Mr. Meji, please. Thank you very much. You may be seated.
Selamat datang di Politeknik Negeri Pontianak, jurusan Teknik Sipil. Jurusan Teknik Sipil Politeknik Negeri Pontianak memiliki 3 program studi, yakni program studi D3 Teknik Sipil, program studi sarjana terapan perencanaan perumahan dan pemukiman, serta program studi sarjana terapan teknik rekayasa konstruksi jalan dan jembatan. Program studi sarjana terapan teknik rekayasa konstruksi jalan dan jembatan merupakan program studi baru di jurusan Teknik Sipil Pontianak yang lahir di tahun 2023. Fasilitas program studi yang didapatkan oleh mahasiswa diantaranya adalah workshop kerja kayu, workshop kerja beton, workshop kerja drainase, workshop kerja baja, workshop kerja batu, dan workshop kerja acuan perancah. Selain itu juga terdapat fasilitas laboratorium yang terdiri dari laboratorium aspal, laboratorium beton, laboratorium tanah, dan laboratorium hidrolika. Ruang kelas yang memadai, ruang jurusan, ruang program studi, dan ruang kerja dosen. Semua fasilitas yang ada telah memenuhi kualifikasi dan standar yang berlaku. Semua program studi dapat ditempuh dengan jalur SNMPTN, SMBPTN, dan jalur seleksi mandiri.
Assalamualaikum warahmatullahi wabarakatuh. Jurusan Teknik Sipil adalah salah satu jurusan yang berada di lingkungan Politeknik Negeri Pontianak. Jurusan Teknik Sipil memiliki 3 program studi, di antaranya program studi D3 Teknik Sipil, program studi Sarjana Terapan Perencanaan Perumahan dan Pemukiman, serta yang terbaru tahun ini adalah program studi Sarjana Terapan Teknologi Rekayasa Konstruksi Jalan dan Jembatan. Jurusan Teknik Sipil juga dilengkapi ruang laboratorium dan bengkel, di antaranya laboratorium
Ladies and gentlemen, we will now begin our seminar. There will be 4 sessions of research sharing, each featuring 1 presenter. Each presenter will have 45 minutes to present their research, followed by a 15-minute question and answer. Before its presentation, I will read the brief curriculum vitae of the presenter. Our first speaker is Associate Professor Insinyur Dr. Abdul Razak bin Abdul Karim, presenting his research, Young Civil Engineers' Role in Overcoming Challenges of Advanced Technologies in Sustainable Infrastructure. To Mr. Abdul Razak is here, obviously.
Yeah, I'm here.
Mr. Abdul Razak bin Abdul Karim, he completed his doctoral study at University of Auckland in 2012, and he is appointed as the member of Asian's Chartered Professional Engineers, one of Panel Evaluators Engineering Accreditation Council Board of Engineers Malaysia. Until now, he is an associate professor of UNIMAS with areas of expertise, structural engineering, aluminum concrete composite, bearing timbers, bolted connections, and non-destructive testing. He has conducted many studies around these areas of expertise, and he received many awards and recognition. To Mr. Razak, time is yours for the 5 minutes presentation.
All right, can you hear me? Hello? Anyone?
Yes, Prof.
Yeah, everybody can hear me, yeah? All right. Okay, Assalamualaikum. Bismillahirrahmanirrahim. Okay, so first of all, I would like to thanks to the chairperson for brief introduction about me. And then next, I would like to express my sincere appreciation to Politeknik Negeri Pontianak, Polnep, for inviting me today as one of the international webinar speakers organized by Polnep. Okay, civil engineering department, Polnet. Okay. Actually, feel very honored to be part of this profound event. Actually, okay. So I believe to address the concern, or more appropriate to say the challenges on the advanced technology in sustainable civil engineering infrastructure, as per stated in the theme of this international webinar. It is very crucial that the young civil engineers to understand how important of their role in creating groundbreaking innovations for ensuring the sustainability of infrastructure in the country. To appropriately captures the theme of this webinar, so allow me to give some general presentation. Actually, it's not really focusing, but if you have focusing on my research, but if you have sometimes, maybe I can share some on my research findings. All right. Okay, so my presentation today will discuss on topic in general, about young civil engineers' role in overcoming challenges of advanced technologies in sustainable infrastructure. All right. So let me share you first the okay. You able to open?
Mr. Rajak, you're
Yeah.
sharing your materials, or we should do it?
Up to you. I can share myself actually.
Or you will share it
Yeah.
yourself.
Okay.
All right, thank you.
Okay. All right. So everyone can see the slides.
Yeah.
Okay.
We do.
Okay. All right. Good. Okay. So before we specifically see on the role of young engineers, okay, to overcome the challenges, so I would like to bring your attention initially to some current technology advancement in engineering field, and maybe we discuss a bit on the challenges in the implementation. All right. So the first thing that we supposed to talk about is on the current technology. All right. Okay, as you can see here, this is one of the current example of 3D printing in civil engineering field. Okay, which you can find this 3Ds to allow engineers to print material layer by layer, and then creating complex structural components directly from digital models. Right. So the benefits of this technology is we can reduce material waste. We can also expedite the construction time, and also allow complex geometries that traditionally method cannot be achieved. All right. So some example that you might also know about this is the 3D printed bridge in Madrid, Spain, which is made of micro reinforced concrete. And then it demonstrates how 3D printing can create complex form with reduced waste and construction time. All right. So additional examples in international level is in Dubai, all right, where you can find the 3D printed office building, okay, by Dubai Future Foundation, was completed in only 17 days, right? This showcasing how additive manufacturing can revolutionize construction speed as well as material efficiency, right? So another current technology that you might also know about smart materials. Okay, so these smart materials are materials that are capable to give positive response to environmental changes. All right, so the benefits of these materials enhances the durability, resilience, and lifespan of structures while reducing maintenance costs. Right, and then some example of it, if you found out, this one is actually developed by self-healing concrete, developed by Delft University in Netherlands, right? Contains bacteria that produce limestone to fill crack automatically, extending the lifespan of concrete structures, right? Another examples of smart materials might be also known by everyone, okay, which is the fiber reinforcing systems on bridges, okay, which is this FRP usage in bridge structural system can reduce maintenance costs and extended lifespan of the bridge. They are also excellent solution for reinforcing existing concrete structures without the need for extensive demolition. And as you can see, also this can minimize the disruption of ongoing operations, such as in bridge or highways. So another that we know about current technology on civil engineering is robotics and automations. All right, robotic and automation are used for tasks in construction for reducing labor dependency. All right, so the benefits of this is we can increase efficiency, improve safety, and also reduce labor costs, particularly for repetitive and dangerous tasks. All right, so example of this that you can see in Australia, okay, robot by the Hadrian X robot by Fast Brick Robotics. They can lay bricks at speed much faster than human workers with precision that reduce material waste, right? So another examples that you might see is in Japan, right? The usage of robots also being done by Japanese construction company, Shimizu Corporations. Okay, they use robots to assist in steel beam assembly and welding tasks in large construction sites. Okay, so another example might be in current technology is the usage of sustainable building materials and also green design. Okay. Okay, so use of sustainable materials like recycled concrete, bamboo, cross-laminated timber, and low-carbon cement. All right. So one of the example that you can see in Bullitt Center, Seattle, Washington, they incorporate sustainable buildings materials and is designed to be carbon neutral with net zero energy consumption, right? So another example might be also very interesting to know is cross-laminated timber, CLT, was used in Vancouver, Canada, right? Which is used to construct the Brock Commons tall wood house in Vancouver. Okay, one of the tallest timber structure in the world, right? So I think another example that we might can see is about carbon capture and storage. Okay, this CSS involves capturing the CO2 emissions, right? which is normally comes from cement production or power plants, and storing it underground to reduce the carbon footprint. Okay, what is the benefits of this is we can mitigate climate change and meet sustainable development goals in construction, right? So some examples, okay, that you can see is in Berwick, Norway. Okay, Heidelberg Cement, a major global cement producer, has implemented CCS, okay, at its plant, so they can reduce the carbon footprint of its concrete products, right? So this is also a landmark initiative that demonstrates the potential for post-combustion carbon capture technology to reduce emission from the cement industry, right? So another examples might be we can see from the Boundary Dam power station in Canada. Though a power plant is also serve as a model for integrating CCS technology to reduce emission associated with energy intensive infrastructure. All right. So in summary of all these examples, all right, these advancements represents significant strides in making civil engineering more sustainable, efficient, and resilient. However, each advancement also bring its own challenges. That is what we're going to discuss a bit on the challenges, which the field is actively working to overcome, right? Okay, so what are the challenges, right? Okay, so one of the challenges might be regarding the high initial cost and investment, because advanced technology such as smart material often requires substantial upfront investment, right? So might be smaller firms may struggle to adopt these technologies due to limited budget. But the impact, okay, high costs can slow down the rates, particularly in developing regions or for smaller projects where stakeholders may prioritize budget constraint over long-term efficiency and sustainability, right? So the second challenges might be about the regulatory and compliance barriers, okay, where standards often lag behind technology advancements, right? So especially with innovation like 3D printing or other or the use of sustainable materials, okay? So approval process for novel construction methods can be lengthy and can cause delaying projects. Okay, so delay in regulatory adoptions can hinder the adoptions of new technologies. Engineers and firms may face compliance issues, right? So which add to project timeline and may increase costs due to regulatory constraint. So the third one might be about the environmental and sustainability concern, okay? Because while many new technologies aim to be sustainable, the actual implementation sometimes has environmental trade-off, right? So for example, 3D printing use specific materials that may not be as recyclable, right? So, and manufacturing sensors for robotics, okay, can generate electronic waste, right? So in striving for greener project, the actual environmental impact of some technologies might contradict sustainability goals, okay, raising ethical and logistical questions, right? So the next might be on the quality control and reliability of new materials. Okay, so smart materials, self-healing concretes, okay, advanced composite may lack long-term field testing compared to conventional materials, right? So questions about durability, reliability, and how these materials behave over decades may remain unanswered, right? So impact engineers may hesitate to use new materials without proven, right, long-term performance data, especially for critical infrastructure, right? So quality control and verification processes are essentials, yet they add additional cost and complexity, right? So another challenge is also on the maintenance and lifespan concern of technological components. Yeah. So the challenge in like sensors, batteries, other components used in robotics, yeah, have limited lifespan and require regular maintenance and replacement. So maintenance requirement add to the operational cost and could lead to lapse in monitoring of functionality if components fail unexpectedly. So ensuring long-term, low-maintenance technology is very important for sustainable adoptions. Okay, so last but not least might be the ethical and social acceptance issues. This is happen when the use of technology such as AI, robots, right, raise ethical concerns, including job displacement, right, privacy, and the impact of automation on the workforce. So public perception and social acceptance play a critical role in technology adoptions. Right? Engineers and organization needs to communicate the benefits and address the potential social impact of these technologies to gain public support. All right. So might be the last things to discuss here is on how the young engineers to overcome these challenges. Okay. All right. So driving cost-effective solution and return of investment awareness. All right. So this is one of the role. By understanding cost-benefit analysis, young engineers can help optimize the balance between initial investment and long-term benefits, making advanced technologies more financially viable. Right. So example of this is conducting case study on the long-term savings of automated monitoring system, for example, or prefabricated components, can help demonstrate the value of these technologies to stakeholders. Right. So another thing is might be the role of young engineers is to promoting innovations and flexibility. Young engineers are typically more adaptable, okay, because they are new generation and willing to experiment with novel ideas, right? So this adaptability is crucial in finding creative solutions to make new technologies compatible with existing processes and overcoming resistance to change. So an example of this might be applying innovative solutions such as modular construction or 3D printed components in projects. Young engineers can test, refine these methods to find practical, cost-effective uses in real-world application and also to comply with the regulatory requirements. And another role that can be played by young engineers is by fostering a culture of sustainability, right? So because young engineers are often more environmentally conscious, all right, and can be strong advocates for sustainable practices. So they can push for the use of sustainable materials and advocates to for design that minimize environmental impact. So encouraging the use of recycle or eco-friendly material is one of the example in any projects, or promoting designs that enhance energy efficiency aligns with sustainability goals and helps address environmental challenges in advanced technology implementation, right? So another role might be promoting quality control and reliability of new materials. Okay. Young engineers can focus on rigorous testing and quality assurance for new material and technologies by participating in research and field testing. They can provide insight into the long-term performance of innovations, materials, and structural elements. Right. So young engineers can work in research lab to test smart materials like self-healing concrete, gathering the data that builds confidence in these materials' durability for large-scale adoption, right? So advancing research and development R&D are also one of the important role by young engineers, because many young engineers are involved in academic or industry-based R&D which is essential for developing reliable data on new technologies and materials. They contribute by exploring ways to improve these technologies and publishing findings that build industry trust. Right. So, example, conducting studies on innovative on technological material or components in robotics, for example, can help overcome the lifespan and regular maintenance or replacement issues, right? So last but not least, encouraging ethical and social responsibility in technology use. Okay, as a representative of the new generation, young engineers often prioritize ethical consideration and can help address public concern about job displacement and automation. So when implementing automation or robotics in projects, they can promote transparency about the benefits of technology in enhancing safety and efficiency rather than replacing jobs. Okay, so to summarize about the role of young engineers, they can contribute significantly by fostering innovations, promoting sustainability, enhancing interdisciplinary collaboration, and embracing new skills. Their openness to learning and adaptability make them ideal candidate to address the challenges of implementing advanced technologies in civil engineering. All right. So to conclude about this general topic regarding young engineers' role, so as we can see here, actually in civil engineering, we have many branches or 6 major areas. All right. So the rapid advancement of civil engineering technologies such as 3D printing, smart materials, robotics, and carbon capture are transforming the construction and industrial practices. However, okay, challenges like high costs, regulatory hurdles, and environmental concerns still persist. All right. So therefore, young engineers have a very, very crucial role to play in overcoming this obstacle. Driving innovations and ensuring these technologies are applied in ways that are both sustainable and socially responsible. All right. So for this part, do I still have sometimes, Chairperson? Any count on the time?
Right, thank you very much, Mr. Rajak. I'm going to read some of my notes here.
Okay.
Right, Dr. Abdul talk about the current technological advances in civil engineering, including 3D printing, the use of smart materials such as fiber-reinforced polymers, and the use of robots in constructions, and the use of sustainable materials and green design. He also discussed capturing carbon and the underground storage of it to reduce the carbon footprints of concrete production. Dr. Abdul also outlined the challenges that young engineers face, covering aspects of technology, compliance, ethical and environmental concern, as well as quality control and product reliability. That was a very interesting and very insightful presentation, Mr. Abdul Rajak. Thank you very much. Now, is it okay we go straight to the question and answer?
Yeah, sure. No problem.
Right, sure.
Yeah.
All right, audience here, or maybe you are the one who's online, please. Yep. Mr. Randy? It seems that Mr. Randy here has questions to Mr. Abdul Rajak.
Thanks. Thank you very much. My name is Randy. Randy Setiawan, and I'm a coordinator of Housing and Settlement Planning and Study Program.
All right.
I have 2 questions. My number 1, what are you use material using for making healing concrete? And we know concrete are made for crushed stone, sand, cement, and water. And what are you used for using in my healing concrete? And question number 2, I'm very excited for quality for 3D printing, for what material for 3D printing. And you know about the bridge must be strength and small deflection, what cause and how to avoid poor bridging in 3D printing, and so prevent the light reflection. Thank you.
Right, thank you, Mr. Randy. Mr. Abdul Razak, to
Okay,
get the
so
questions? Yes.
let me try to repeat the questions so to ensure that I understand your questions. All right. So first one is on the, but you more concerned on the material used in healing concrete, right? And then the other one is material also in
3D printing.
3D printing, right? Okay.
And what cause and how to avoid poor bridge in 3D printing, and so prevent the large deflection.
Okay. So let me start with the material used in self-healing concretes, right? Honestly, I'm not the expert on this area, but through readings, we might can see the material is actually they use some bacteria and calcium lactate. All right. How it works? Okay, so this method use like spores of bacteria. Okay. The typical species used is a bacillus species. All right. So they embed in the concrete mixture, and then along with a nutrient like calcium lactate, right? So and then how do they work is when the crack form, okay, and water enters the concrete, so the bacteria become active, right? Okay, and then consume the calcium lactate as their nutrient, right, and produce limestone, right, calcium carbonate, which acting to fill up the cracks as a seal. That is how in generally they do it. Okay, you can find in any journals, I think, on the self-healing concrete. But I think one of the speaker today is going to talk about self-healing concrete, if I'm not mistaken. Okay, might be he is the one that more appropriate to talk about this topic. Okay, but in general is something like that. Okay, all right. So on material 3D printing as well. Okay, honestly, I am not the expert as well. All right, but wait,
All right.
okay, so the 3D printing normally they use in construction for the use of structural architectural applications. Okay. They use variety of materials. Okay, depending on the project requirement, but might be some of it might be I can share with you. Okay, they might use sort of like we know about this material actually, geopolymer. Okay, it's inorganic materials. They're made from industrial byproduct like fly ash, okay, or slag. Okay, and then using activated alkaline solutions, right? So that's why sometimes all these materials is become because you are asking as well about the cost, right? So it's become costly because of we have some additional solutions like this activated alkaline, right? But it's very suitable for the use of 3D printing. Okay, and then some of it might be another material like our normal concrete and mortar mixes. Okay, that they can be used as well. And then another one might be foam concrete. Okay, foam concrete because they are lightweight and also incorporates air bubbles, making it lighter than traditional concrete. So I think that is more or less in general about the material, but I cannot give you specifically about the costing on it. All right. Okay. It depends on the types of materials that you use and types of alkaline activator. Right. I hope I am answering your questions, your two questions. Right. Yeah. But not in detail,
Sure.
but in general might be. Yeah.
All right. Mr. Randy?
Yes, thank you very much.
All right. Thank you
All
very
right.
much, Mr. Rajat.
Yeah. Yeah. Thank you as
Is
well
there-
for Mr. Indy. Yeah. For the
Is
questions.
there any other question from the audience here or maybe the ones online? Please.
Thank you for the opportunity. My name is Risa. I'm from Department of Architectural Engineering. It's very interesting to be here today to listen to your presentation. There's one question that I'm quite intrigued to know. Are there any studies that summarize about the measurement of what the young engineers should do to overcome the challenges that you just stated in conclusion? Thank you.
How should I say? What is other? Can you repeat again the question? Sorry. What is other?
Are there any measurement like something that we can measure, like
The measurements.
yeah, the measurement. Like
Okay.
you stated that the role of young engineers to driving cost-effective solution, promoting
Okay. All right.
innovation,
Okay.
etc. Are there any measurement that we can know? Are there any studies that stated the measurement to know if the young engineer successfully, let's say, promoting innovation
Okay.
and etc. Thank you.
Okay. So might be I give you just a few role of young engineers, right? That is what I understand. And then you want to know some more measurements that might be the role of young engineers to overcome all these challenges. So actually it depends on situations, okay, that you are facing. Like if you having problem in something like in IoT, for example, right? You have to you have very old versions of software, for example, in designing structural system, for example. Okay, so as a young engineers, they are more intrigued to this gadget and also these software things, these IoT things, okay, Internet of Things. All right. So might be they can learn the new technologies because they still have this dynamic and enthusiasm, okay, and also can bring the knowledge and emerging the tools and methodologies by do some sharing session with another young engineers, okay. So making them to be up to date by this latest technology or materials, or might be engineering practices, okay, new methods in constructions can bridge the gap of traditional method and modern advancement. All right. Example might be gaining certification in building information modeling. Okay, people are talking about BIM right now, right? And then all these young engineers, they are very interested in knowing all these things. Okay, so learning program language, okay, like MathCAD or some other softwares like Esteem, eStep, and so on, right? They might be the one that can what we say, that can innovate the current softwares rather than just like us as a end user of the software, right? So This is how they can play their roles depending on the issues. Okay, so the most important thing is actually how do we find the issues, and then how do we put our role into it to overcome the issues. Okay, another examples might be if you find some issues in enhancing data literacy and cyber security awareness, right? So these young engineers who understand about this data analytic and cyber security principle can help address these challenges. Okay, and then managing vast amount of data and protecting the sensitive informations, right? So for example, if the engineers is working in IT departments, okay, he got some good knowledge about IT, right? So he can help the department to ensure the data from the IoT device, okay, used in structural monitoring, for example, is secure, okay, and then ensuring the data integrity, and then preventing unauthorized access to critical infrastructure data. Okay, so because our design sometimes is very private and confidential, so by having this kind of knowledge, they can actually solve the problem. Okay, if you want to talk about another issue might be in terms of when we want to innovate something. Okay, we need also to develop a mindset of lifelong learning, right? That is another attitude that we need to instill to these young engineers, because the rapid pace of technology advancement, okay, normally requires a commitment to lifelong learning, because we are, even though we have, for example, we have our highest degree, we still need to learn because of this technology keep on changing, right? And then these young engineers at the beginning of the career might be not really that skillful, but they are actually well positioned to adopt a mindset, okay, and keep them updated with the latest technology development, right? So how to do this? Okay, we encourage these young engineers to attending conferences, because we have some networks there, experts are there, and then we can mingle with the experts, and then also keep on advancing your career by enrolling in professional development programs, like, and then pursuing additional certification to have the qualification in the fields. Okay, like right now people are talking about AI, machine learning, right? So we can reduce some experimental way to find the solutions by using this AI and also machine learnings, okay, to process the data and come out with some predictions, for example. Okay, so I hope by adding a few issues, and also the role of how these young engineers can help the country to play the role, okay, to the challenges of this rapid advancement in technology, especially in civil engineering. So I hope I'm answering your question, ya, Ibu.
Yeah,
Right.
thank you.
Ya, terima kasih.
Thank you very much, Mr. Abdul. Thank you very much.
Ya.
Right. Is there any other questions for Mr. Abdul? Is this a great opportunity to, yes, since that we have someone raise their hand here to.
Thank you. Let me introduce myself first. My name is Dinda. I'm a student of Politeknik Negeri Pontianak. I'm from Department of Civil Engineering. I'm curious about 3D printing. There's one question. Is the 3D printing affects the climate change? If it yes, then how that will be? Thank you.
You mean the material that we use in 3D printing is affecting the climate
Yeah,
change?
yeah.
Am I correct?
Yeah, the
Okay.
materials. Yeah.
Okay. So the materials, I think I have mentioned some in my presentation just now. Okay. So because that is actually one of the challenges yang saudari bertanya tadi kan, because some of the material is not recyclable material, right? It's not eco-friendly material. They are very limited material to be used in 3D printing, for example, right? So that is the challenges for you as a young engineers, okay? And then the material might we can say might affect the climate change, right? Because we are still depending on like cement productions. It's caused the CO2 emissions, and then our manufacturing factory is not implementing this CCS, carbon capture and storage, right? So it's still exposing the country with the CO2 emissions, right? So I have mentioned this example in my presentation. So I do agree with you. Some of the material is not really that eco-friendly material, and it's not really a recyclable material. But that is the challenge for us to produce or innovate materials that can be used in 3D printing, but as well as to be environmental friendly material. Okay. So I don't deny that, because might be the current technology is not really that environmental friendly, but we need to keep learning, to innovate, and to create some new materials, more smarter material might be, okay, to more reflecting the climate change that is also our problem right now, right? So I hope I am answering your question. Okay, all right.
Right.
Thank you, Mr. I'm sorry.
Yeah, thank
Thank
you
you,
for your
Mr.
question as well.
Abdul
Yeah.
Mr. Abdul Rajak, we have question here from audience online. I'll read it for you.
Oh yeah.
I am R. Puspito Harimurthy from the Departments of Architectural Engineering. There are a
Okay.
few things I want to ask. The first is, what is the level of sustainability of the use of this new technology in several countries with similar regional characteristic, Asia Pacific, that have adopted it? Is there a strategy for dealing with the 6 challenges mentioned above, especially related to social and ethical response issues as a precedent?
Right.
Right.
The question is very tough. Yeah, I need to be a president of a country to answer this.
Yeah.
Okay, but it's okay. It's okay.
Well,
We
anyway,
try.
at least we try. At least we try.
Yeah,
Okay,
at least we
thank
try.
you,
But
Mr.
it's
Abdul
a
Rajak.
very
Yes.
it's a very good question. It's a very valid question. Also the same with other questions given by other audience just now. Okay, so I may I repeat again the question? What is the level of sustainability, right? And then the use of this new technology in several countries. I read again the questions. And then with similar regional characteristic. And then he specified, I think, is R. Puspito is okay. She right? Am I correct?
Yeah, by the name probably he.
He. Oh, sorry.
He.
All right. Okay, so he also mentioned about Asia Pacific. That have adopted it? And then is there a strategy for dealing with the 6 challenges mentioned above? Okay, especially related to social ethical response issues. Okay, maybe I give you one example. If you talk about Asia Pacific, I give you one example just now on Japan, right? They use these robots, okay, automation in assembling steel beams, right? So instead of they're using human, maybe with a common machine that controlled by human, and then they use this what do we call these robots, okay? And then if you can actually negotiate, or actually in ethicals or social responsibility, right? You might raise the concerns when you develop this kind of technology. You might raise the concerns of the public that they will lose their job, right? Okay, so the things that might be in negotiation, maybe we need to highlight more on the safety precautions. Okay, instead of people doing the assembly of the steel beams, it is good to let the robots doing it, and then the human is just the person who need to monitor if anything happen to the robots assembling process, right? So he or she is not losing their job. Actually, it's actually more on monitoring rather than doing the things. Okay, and then also will more protect them from any danger or failure, anything on the machine that they control on site. Okay, so let the robot do it, you monitor it, and then it helps you by doing some repeating jobs, for example, and some heavy jobs and some danger jobs. And then like this welding, also there some company is using the robots to doing it. Yeah, it's actually protecting your eyes. Okay, because you can just monitor from far away from the things that you want to weld it, right? So maybe that is one things. Okay, examples that maybe we can say we as the one who innovate the technology, we need to embrace more on the benefits on the social and also the safety parts to benefits the humans. Okay, because robots can be replaced, but human is not that simple, right? Okay, so might be another examples might be in Singapore, maybe. All right. Okay, so because Singapore is one of the leader in adopting 3D printing for constructions, right? So they focus on using sustainable material. Okay, because you also asking about what is the level of sustainability. Okay, so it depending on how you innovate the things, greener material use will be more environmental friendly, and then will be, but you need to as well test their sustainability in terms of their strength and so on, right? Okay, so because in Singapore they use recycled concrete, okay, and also fiber reinforced concrete, fiber reinforced composite, sorry. Okay, so they promotes research, okay, in these sustainable constructions, okay, and then they use this 3D printing aligned with their green building master plan. Okay, so they have their own guidelines about the green building. Okay, so the reason why, because they want to reduce this construction waste, energy waste, okay, and also carbon footprint. Okay, so the level of sustainability can be increased up to the level of might be if you have a guideline or standard, you can refer to that. How to have a greener or green building, for example. Okay. Maybe each country have their own master plan. Okay, so if you might be not all components in the building are greener, but some of it to achieve some part of the structural system might be the foundations, maybe, right? And then in China as well, okay, if you they also use this 3D printing technology, okay, especially for low cost housing, okay, issues, okay. So they use this 3D printed for entire house using sustainable concrete mixes and also incorporate industrial waste. So as you can see there, when they said sustainable concrete, might be the concrete has already been innovated to become more environmental friendly. And when you incorporate the industrial waste, meaning that you are solving issues of abundance waste in your country, right? Okay, and then like normally we have this problem of abundance fly ash, right? And then reducing raw material use in landfill dependency, right? So might be another one, might be I give you one example, might be in Australia. Okay, they also use this 3D printed housing and infrastructure. Okay, the use of this is to address housing shortage and promote sustainable construction to their country. And then the concrete that they use is geopolymer concrete, okay, and a low carbon material. Okay, so that is the things that when you have a better material, you can increase the level of the environmental friendly level and also the sustainability of your construction. Okay, because they have their own goals. Okay, in Australia they have their own objective on achieving the sustainable development and also to promote the climate resilience in their country. Okay, so actually it's depending on the master plan of the country as well. Okay, if you have a good master plan, we follow the master plan, we innovate some things to follow the master plan, and then we might be a country that environmental friendly and also sustainable and resilient country in terms of constructions and especially in civil engineering practice. Right? Okay. So I hope in generally I'm answering your question, yeah. Right.
Right. Okay, Mr. Abdul Razak, thank you very much. And then I think we have completed our first session. Thank you very much, Mr. Abdul Razak, for your presentations, which actually give us ideas of what these young engineers may have to face in the future, the challenges, and also it inspired all the lecturers to a new way or new insight or ideas how to prepare these young engineers to face challenges. Thank you very much, Mr. Abdul Razak.
Yeah, thank you for the invitation and salam kenal untuk semua.
All right, you ready for the second presenter? Yeah. Now, our second speaker, Associate Professor Dr. Insinyur Ling Chenhua. Right. Mr. Ling Chenhua.
Yeah, I'm here.
All right. Okay,
Yeah.
excellent. Now, would like to read your CV briefly. Associate Professor Dr. Ling Chenhua, he completed his doctoral study at University Technology Malaysia in Johor. Until now, he is an associate professor at University of Technology Sarawak. He is an internal auditor of UTS ISO 9001-2015 He is the head of the Center for Research of Innovation and Sustainable Development, UTS. He received many research grants and also awards. Please welcome Mr. Ling Chenhua with his presentation titled Concrete Field Tubes or CFT as Compressive Structural Elements. Dr. Ling, please.
Yeah, good morning, everyone.
Good
My
morning.
name is Dr. Ling Chenhua from University of Technology, Sarawak. And
Okay, good
I'm
morning.
really honored. Yeah, can you hear me? Sorry.
Yes.
Okay.
Yes, you could. Thank you.
You
Quite
can
clear.
hear me, huh? Okay. So I'm very honored to be invited as speakers for this event. And today I would like to share my topic on the concrete field tube, CFT, as the compressive structural element. So before we start, let us go through the content. We're going to cover the introductions about CFT, and then the applications of CFT, research on the CFT, various types of CFT, the behavior of CFT, the prospects and future studies, and conclusions. Without further ado, let us get started. So, first of all, what is CFT? Concrete field tube is a composite column that is made of concrete plus the tube. So this concrete and the tube, they work together in order to achieve the greater performance of the structural element. Now, as you can see here, by having the two combinations of different types of material, each playing their different roles in the structural element, this can give us the higher axial strength, higher ductility, greater energy absorptions, and also higher post-peak strength. So now let us look at the mechanism, how they work together. First of all, we look at the tube. Tube itself is relatively slender in terms of the thickness of the tube. And when subjected to the axial loads, it is susceptible to local buckling. There can be inward buckling, and they can be inward buckling, and they can be outward buckling. Now, as for the concrete, under axial loads, crack tends to develop, and eventually it forms the shear cracks. By having both materials in combinations, the concrete helps to prevent the inward buckling, but this cannot fully prevent the outward buckling. And then as for the tube, it helps to provide the confinement forces in order to control the cracking developed within the concrete. As a result, it gives you a delayed local buckling and higher axial strength. So here, what you see here, in principle, if we are designing it properly for the CFT, you will have 1 plus 1 more than 1. That is the main reasons of doing this CFT. Now let us talk about some concept about the confinements. First of all, you know the concrete materials. When it is subjected to compressions, it tends to shorten and expands laterally. This happens when there is no confinement acting onto the concrete. Now, in order to ensure this confinement is in place, you need to make sure that the concrete expansions will be greater than the transverse strength by the tube. When subjected to the load, tubes also have the tendency to go expansion. Now, you need to prevent the tube from excessive expansions so that the relative difference between the concrete expansions and the tube expansions will create a situations of biaxial or triaxial state of compressions. This helps to improve the performance of the concrete when subjected to the axial loads. So that is the fundamental principles behind the adoptions of this CFD. Now, other than that, there are other advantages. First of all, the tube itself can be a stay-in-place formwork. This is going to reduce the cost for you to adopt the formwork and also save your time in terms of preparing those formworks, because after the constructions, the tube will stay there as a part of the structural element. Another thing here is tube also helps to prevent the moisture loss during the casting and during the curing period. This allows for greater quality of the concrete. Now, we all know that tubes confines of concrete, it will give us better strength and ductility. Other than that, it also gives you a greater durability. Particularly, it protects the concrete from the thermal changes and also moisture penetrations. Especially, it creates a barrier to prevent the chemical attacks or exposures to moisture that can lead to the damage of the concrete. Now, let us talk about the applications. As far as we know now, CFD is quite common among the high-rise building, bridges, and subways. As of 2018, I took it from one of the paper here, China has constructed more than 400 bridges using CFD. And the biggest span of the bridge can achieve 530 meters. Now, I believe by now, 2024, it will be more, but I haven't encountered the relevant paper yet. Okay. And these are also some projects adopting the principles of adopting the technology for CFT. Now, you see here, CFST here is actually stand for concrete filled steel tube. Concrete filled steel tube. It means that the tube is made of the steel. And this is among the most popular CFD currently being in use due to its reliability and the quality of the resistance provided by the tube. These are some photos regarding the CFD. And you can see the size of the members as compared to the size of the person, and also the construction process. Now, so far I have the photos that taken from the internet, mainly on the steel. So I believe this is still currently dominating the CFD view in the construction, the steel. And then we have the joints, how they do the joints for the CFD, and how they do the joint to the support also for the CFD, and mainly on the steel. Okay, now let us talk about a bit on the research on the CFD. So I did a bibliometric analysis where I extract the papers by using this search command. So basically, the purpose of the command here is to filter out the CFD that is subjected to the axial or compression force and focusing on the static loads only. So other than that, because of the scope of my study, so I discard those and did not consider that. And I took it from the Scopus database and for the past 10 years publications. Now, the first search command here give me 1,700 something publications. Later, I limit those to engineering, material science, journals, articles. I disregard the conference papers and English medium, and it give me 1,154 publications. And then we plot this here. You can see now the publications and the citations is actually increasing over time at exponential conditions, right? So what you can see here, it seems that this relevant research now is gaining momentum. now more and more people are interested with this CFT technology. Now, why is it in 2014 here there is a sudden drop here? It is because I did that in August 2024, which is quite recently. And the data only cover up to August. So if we consider this whole year, probably it will be higher. It will be the highest of all the recent 10 years. Okay. Now, also, knowing the relevant studies now, you might want to know who are the main players, right? So we also did some analysis in terms of the authors. Now we do some co-author analysis here. So let me share with you how do you read this. First of all, you look at the color here. The brighter the color means that the more recent the publications. The bigger the bubble size means that the higher citation rates. And the linkage, you see the lines here. The linkage shows that they co-author together. That means they're writing the papers together. And then those in the bracket means the numbers of the researcher in the clusters. Okay. Now, having this understood, now let us look into the content of this. Okay. Let me readjust. Yeah. Okay. Let us look into the content of this. You see here, this is a really big group of clusters, which comprising about 9 main clusters here. And this means that there are researchers not only working within their own clusters, they also work together with the other clusters. So they work together, and that means they have formed their own network already, which they are interconnected. And also you have independent clusters. These clusters do not have connections with the main clusters here, but they form their own clusters as well. And then you see the color here also, this one seems like dormant clusters. It means that they do publications and they are the pioneers in the field, but they don't have recent publications. And also you see emerging clusters as well. This one is they are not the pioneer, but they are start becoming active recently. So these are emerging clusters, but at the moment they don't have any connections to the main group here. And it is interesting to observe also there are combinations of the pioneers and the recent researchers. So we call this as the evolving clusters, which is quite healthy in terms of the technological transfer. And also you can see the mentorships. By looking here, I guess it is quite easy for you to identify who are the big players. Okay, so you will see those big names here. So theoretically, if you're supposed to do research on the CFT, probably you might want to look into those big players as well. Make sure you do not miss the important fundamental of it. Okay, so this is about the research on the CFT. Now, let us talk about the top 10 publications country here. And number 1 is China. And it is interesting to find that China alone, the total publications is actually greater than the summations of the rest. And number 2 to number 10 total out still less than China. So you can see how aggressive in terms of their eagerness in this technology. And you also see that China has invested a lot of resources in CFT. And out of the top 10 research funding agency, 8 is coming from China. So you see why they are so eager with that means their involvement in this CFT field. So it means what? It means if you are doing studies on CFT, probably you might want to also look into the research publications from China as well, okay? Because they have a lot of research related to the CFT. Next, we talk about the types of CFT. We have basic type of CFT. This is the earliest form of the CFT. You have concrete, you have tube. So that forms the most basic types of the CFT. And then we have CFT with internal reinforcement and CFT with external reinforcement. The internal reinforcement, you can have steel, such as the reinforcement for like conventional columns or the steel sections. As for the other type, you have internal tube or the field tube. As for the external reinforcement, on top of the basic CFT, they have extra layers of protections. This outer layer here can be made of other material such as FRP, and also it can be concrete. And this one is the protective layers applied throughout the member. This one is you have alternate protective layers. It doesn't apply throughout, but it's going to apply partial to the CFT. Now, having this, because of the variety of the design, it will end up with a lot of different names for the CFTs. So they name it differently. Now, what you can see here, these two looks similar. The difference, it will be the void within inside. So they call it differently. One is called double skin tube, another one is called double tube. Now, bear in mind that this CFT, it does not necessarily always be circular. It can also be rectangle or square, and can even go for other shapes such as octagonal and etc. Okay, there are quite a variety of the CFT. Now, personally, out of so many designs, my preference here is I would prefer not to have the internal reinforcement, something like this. The main reason here is the rationales of us doing the CFT here is we want efficient constructions, right? So we don't want to go through the process of preparing the reinforcement as an internal, and that will consume times. That will consume times and extra costs. Now, if we really need those internal reinforcement, probably we will look into something which is easier, other than a lot of work that you had to tie the reinforcement, you had to put those reinforcement in the right place, and so on and so forth. Now, in the case that you have this internal reinforcement here, one extra conditions you have to consider is you need to allow sufficient space for concrete casting, because you might have issue with the improper compactions, which you never know. You cannot see what's happening inside after after you've done the casting. There may be segregations, or there may be honeycomb within the CFT. So that one you're not sure. So at the end of the day, my personal preference is the simpler form. It would be to me, this is my personal preference. Okay. Now, here I have summarized quite a number of materials nowadays researcher has used to produce CFT. Actually, we have more here. I just highlight those which are quite common here. And for the tube, you have carbon steel, you have stainless steel, you have aluminum, you have FRP, fiber reinforced polymer, and you have plastic. As for the infill, you can have normal concrete, you can have high-strength concrete, self-compacting concrete, lightweight aggregate concrete, foam concrete, fiber reinforced concrete, geopolymer concrete, recycled aggregate concrete, and etc. There are so many variety of the materials that can be used. Now, if you search through the literature, you will find really a huge potential here. It is very easy at this moment. It is very easy for you to identify the research gap, because there are so many possibilities that you can deal with the combinations, and some combinations at the moment probably have not been fully tested yet. So there's a huge potential in terms of the research field This is as far as what I have observed. Okay, now by looking at so many materials here, it may seem to be very complicated, but at the end of the day, it goes back to the engineering properties. For example, the mechanical property, the physical properties of the material being used. For example, we are looking into the modulus of elasticity. Why is it so? Because modulus of elasticity talk about the deformations against the load. So that level of deformations, it will influence the confinements acting onto the concrete. We also look into the tensile strength because you are looking at the concrete undergoing expansions and the tube resisting these expansions. So this will cause a situations where the tube will be undergoing the tensile stress. So here we also want to, we also need this tensile strength here as the transverse tensile resistance. And we might want to look into the compressive strength as well because it's also provide axial resistance and also the ductilities that will influence the energy absorptions related to the survivability of the structures and buildings. Now, you can see here, still these properties, most of the properties are very high. And fiber reinforced polymer, you have modulus of elasticity and tensile strength high, but compressive and ductility relatively low. And plastic, theoretically, most of the items are low, but here it's written high here because after the peak, this have certain post-peak ductility here. So I put it high here. So what you can see here, different types of the material, it will give you different behaviors of the CFT. For example, for typical concrete without any tube, it fail in the brittle manner. Now, if you use fiber reinforced polymer tube, the strength is higher, but it's still to a certain degree of brittleness. Now you have steel tube also, this one better. It have high ultimate strength. Also, it have really high ductilities. As for if you're using PVC tube or plastic tube, the brittleness here, how do we address this? The ultimate here come with a low ductility, but it has high ductility after the peak, post-peak ductility, that what we are talking about here. And sometimes we need this for the survival purposes, just that it's already exceeded its peak conditions already. So now by looking into different properties here, it will influence the behavior of CFT not only by this load displacement or stress strain response. There are also other considerations. For example, the material, whether it is corrosion resistance, and probably the aesthetic views, or will you like it to be lightweight or what? And also aluminum and stainless steel may have issue with the poor bond with the concrete. Now, bonding to the concrete, infill concrete, is not an issue when the member is predominantly subjected to the axial force. But in the case that you have eccentricity load or the member is subjected to flexural bending, now the bond starts to become quite important. So in terms of the selections of material, these probably are some other things that you might want to consider. Okay, now let us quickly go through the different types of the materials. I might not go into deep every single one of it. I just, to make it simple, high strength concrete, normally we have high elastic modulus. Now having high elastic modulus means that the rate of deformations under the load, it will be relatively low. Now when the rate of expansions is lower, it is slower to trigger the confinement effects within the CFT. So, but you have advantage higher axial strength. So this leads to, two important things that driven the capacity or performance of the CFD. One is high axial strength, another one is high confinement effect, right? But now if you're using high strength concrete, have high axial strength, but the confinement effect, it will be slightly reduced, slightly. Now, let's say if you're using the self-compacting concrete, self-compacting concrete is good for the compactions, but because of its high cementatious materials and low water cement ratio, it may have issue with the shrinkage. Now, shrinkage, why is it going to be an issue? I guess I have a slide here to share with you why is it so. Now, if the concrete inside undergo excessive shrinkage, it will form a gap between the concrete and the tube. Now, what's going to happen later means that you need the concrete to expand first until fill the gap. Only then the confinement effect starts to trigger. That means the confinement effects response, it will be slightly lower if you are using those experiencing high shrinkage rates in terms after the hydrations. Okay. Now, also, that a typical concrete typically will undergo shrinkage. Now, if you want to prevent that, probably you can use expansive concrete. Now, based on my personal observations, at the moment, not many papers I encounter related to the expansive concrete in CFD, but there are many papers on the expansive concrete itself alone. Now, theoretically, it seems to be viable because the expansive concrete come with two mechanisms, either to minimize the shrinkage or to encourage the expansions. This is going to prevent the situations where there will be a gap in between. And this straight away, in the first place, it will be more efficient in terms of triggering the confinement effects within the CFT. And then next is about fiber reinforced concrete. The principles of doing this fiber reinforced concrete because you would like those fibers to help you to control, restrain the crack. As a result, it will have lower creep and also lower shrinkage. At the same time, because of this restraint given by the fiber, not only it reduces the shrinkage, it also reduces the expansion rate. So at the end of the day, there are also plus and minus in between. But you will see that the enhancement in terms of the axial capacity is much more influential in this kind of CFD with fiber reinforced concrete. So that is the main reason of those. Okay. Now, other than that, there are also sustainable materials such as the geopolymer. You have recycled aggregate concrete. Some even use seawater, sea sand, and even coral aggregates as the concrete. Now, geopolymers are eco-friendly because it does not produce heat and also it gives you low carbon dioxide emissions. Now, so far, the papers that we encounter here is the performance is not consistent. The strength enhancement is not really directly proportional to its strength. So at the moment, probably there's still a long way to go to further study about the applications of geopolymer in CFD. And also recycle aggregate concretes, they may seem to be eco-friendly, but at the moment it is not really economical because you need energy, you need extra labors and costs to process those recycle aggregates. Okay, and this recycle aggregates has other issue, for example, the high porosity, which can absorb more waters. So you have to be careful in terms of the water cement ratio later. And probably it might lead to the lower workability and strength eventually. Okay. And how about the seawater, sea sand, and coral aggregates? I saw some research on that, but there are some concerns related to the chloride content. that can be quite corrosive to steel. And also there are rough and porous surface which will affect the qualities of the concrete. Okay, so what you see here, you have so many variety of the materials that potential being used, and researchers have tried various type of their creativities. Okay, now this one we have already discussed. We are looking into the stiffness, the yield strength used for the design, the ultimate the peak strength used as the safety measures, and also the strength softening period here. After the ultimate, if you can prolong this one, it gives you a greater survival purposes for the structures. Now, in terms of the failure modes, these are some common failure modes. For example, shear failure. This occurs within concrete, where you have so many micro cracks develop within, and eventually they come together and give you the shear failure, shear plate. And then as for the drum failure, it occurs when concrete undergoing crushing and also excessive lateral expansions. And buckling, it happens when you have high slenderness, and also dilations or fractures happens when the tensile strength of the tube is relatively low that cannot control the expansions of the concrete. Where you have this hook means the horizontal transverse hook stress is higher than the tensile stress of the concrete. These are some examples of the failures that you can encounter in the lab if you do the test specimen in the lab. Now, let us talk about the analytical part of this design for the CFT. If you look at the research here, there are two main types of two categories of the derivations. One approach is using the principles of superpositions, where the CFT axial capacity is assumed to be equals to the summations of the concrete plus the tube. Okay, now this one have also some limitations. For example, this one does not consider the influence of the slenderness, because you know when it becomes more slender, now the tensile capacity will be degraded. And it also did not really consider the influence of the confinements, because you assume this one and this one plus end up is going to be equal to the CFT. Okay. Now, the second approach here, they use the principles of confinement by having the confined concrete strength equals to the unconfined concrete strength plus the confinement effects. Okay, so this confinement effects require the researcher to use a lot of empirical data. That means they do a lot of testing in the lab, and then through statistical measures, they work out this K1 here in order to estimate the concrete, the confined strength of the CFT. Now, this approach also has some limitations. First of all, you need a lot of data here. And this K1 here is very refined to certain specific applications. You might not be able to use the formulas for the other situation. This is very custom made to the situations that the researcher who proposed the equations very confined to their applications. And one more limitation here is this K, because you use the statistical approach to acquire those, you don't know what's inside this K here. There may be a few other factors, but it's not fully quantified, but you just lump them together into one K as the coefficients. So far we have encountered, personally, I see two main approaches that they use in terms of predicting the axial capacity of the CFT. Now, this one shows the examples, different researchers, and they are giving you different case. Okay, some even modify slightly the formulas and eventually give you, but at the end of the day, if you really want to adopt their formulas, you have to look into their conditions, so and also their boundary, their scope of their studies, the boundary in order to get the more reliable predictions. Okay, now let us come to a very important part here. It's about how do we understand the fundamental principles regarding the CFT. So this diagram here summarizes the whole thing here. First of all, what you can see here, we want the CFT to be high axial load capacity. Why? Because this can give you a higher design strength. We also want it to have high energy absorptions. That one is for the survival purposes. And also we want it to have high durability because this can give you a longer lifespan. Now you also see some components here, they are interrelated. For example, if you have effective confinement, you will get higher load capacity and you will have higher post-yield strength. And which higher post-yield strength can give you higher energy absorptions, and high ductility also can give you high energy absorptions, and so on and so forth. Now, you see we categorize here in two different types of materials. This one is for the tube, and this one is for the concrete. The requirement for the tube and the concrete leading to these effects onto the CFT. Some they are consistent, some they are not. So we're going to look into in detail on this. First of all, if you want the CFT to have high load capacity, you will need the tube to have high axial resistance, and you also need the concrete to have the high axial resistance as well. So having those, because the principles here, principle of superpositions, is the summations of both. Okay, now you know that in most of the study here, they have indicated that the concrete is still dominant in terms of the resistance to the axial loads. Okay. So concrete is still dominant in this case. So if you would like to significantly increase the axial strength, probably you will look into the concrete part. Okay, next we are talking about the confinement. Now, confinement here, first of all, you need to know that in order to have confinement to be in place, there are two conditions you need to fulfill. First, the expansion rate of the concrete will need to be higher than the expansion rate of the tube. Okay, and second, there shouldn't be any gap between the concrete and the tube. It is only when these two conditions is fulfilled, then the confinements will take place. Now, previously we talked about you have so many different materials here, right? Because of their material properties differences. Now, the variations will happen when the confinements start taking place. Some even can have the confinement after the peak strength. Some they can trigger earlier. So it depends on the materials that you're using. Okay, so to make it simple, you want this to undergo slow expansion, and you want the concrete to undergo higher expansion. Now, what control this expansion? You are talking about modulus or elasticity. So at the end of the day, you are looking into the tube with high elastic modulus and concrete with a lower elastic modulus. Now, how do you get the concrete with low elastic modulus? You are looking into normal strength concrete. Okay, high strength concrete, you give you high axial loads, but the confinement effect will be slightly lower. Then you're going to do some fine tuning in order to give you the best performance of the CFT. And the second one here is you want to prevent the gap. So you need to reduce the shrinkage of the concrete materials that we use. Okay, next we talk about you want also the effective confinements. Now, another factors that affecting the confinements, it will be the stress. Now, your transverse stress of the tube needs to be greater than the greater than the force required, stress required to resist the expansions. So it is only, it does not fracture, then the confinement it will take place. Therefore, you will need the tube material to have higher tensile strength in order to achieve that. Next, how about the ductility? So you like both materials to have high ultimate strength so that it gives you a higher degree of ductility. And then you want it to have to be more durable. So durability is, for example, like steel tube here, you may have issues with the corrosions. You have to prevent the corrosions, have to come up with some measures, or you replace with some other materials that are resistant to the corrosions. Okay, so having this fundamental principle understood, so now it make clear, it make you quite easy to understand no matter how you change the material, as long as you go back to their engineering properties, more or less you can predict, you can understand how it's supposed to respond. So to make it simple, now the underlying principles for you for the tube here, these are the strategies that you can use in order to improve the CFD performance. As for the concrete, these are the strategies that you can use in order to improve the performance of the CFD. And to make it simple, you want the steel tube to be strong and rigid, and you want the concrete to have the ability to expand in order to trigger the confinement. But you want to prevent the shrinkage, or you want to reduce the shrinkage. Okay, otherwise expansion alone might not be sufficient. Okay, so if you understand all this one shouldn't be an issue. Okay, so these are some strategies. Other than the materials governing the performance, there are other factors also governing the performance of CFD. So the researcher also into some other areas how they can improve the performance. Now, the study shows that if the loads is applied onto the concrete only, the performance of CFD, it will be higher than they apply both equally on the concrete and the tube. The reason here is if you apply Asian loops to the concrete only concrete undergo expansion. Tube does not undergo expansions. Now, by having this, you can trigger the confinements where the tube act as the resistance to the expansions of the concrete, giving the concrete an triaxial or biaxial states so that you improve the performance of the concrete. Okay. Now, in order to achieve that, researchers come up with 1, 2, 3, 4 solutions to mitigate this, to create such a conditions. For example, extended concrete, which you do not have tube throughout. You extend the concrete a bit so that when you apply the load will only happens apply to the concrete but do not apply to the tube. Another one, they use this gap here. At certain intervals, they create this gap. So when the load is applied onto the members, there is a discontinuity in terms of the stress applied onto the tube so that you will concentrate more stress within the concrete. Or you can have bearing plates here covering only the concrete but not onto the tube. Then you also create a similar response. Or you can provide the partial loading conditions by having the more higher stress in the middle and then lower stress towards the tube here. So these are several conditions here that the researcher proposed that they can manipulate how you can maximize the performance of the CFD over the same materials. Next, in terms of the research, there are many load conditions that you can simulate. This one is a concentrated load. You can also have the situations of the uneven loads, which can give you the fractional bending over the member. It can also have eccentricity load, and also under high slenderness, you will have second order effects onto the members. So you have quite a lot of opportunity to study on that. My personal observations, at least based on what my personal literature review, most of the study, they do simple specimens, small size, small scale specimen, something like this, small scale specimen, and they do it pure axial. So you still there are a lot of studies that can explore for different variety in terms of the load conditions. Okay, now let us talk about the prospects and also future studies. From the bibliometric analysis, it is very interesting to notice that there are a few research, okay, start using this machine learning, okay, in order to predict the CFD response. I find it quite interesting here because those are at the cutting edge technology while we are still wondering how do we deal with the analytical from the fundamental approach, some researcher they start venturing into this field. I believe this is going to be the future trend. Okay, I'm going to finish soon. Okay, so you can see this is, I believe this is going to be an emerging trend in futures, and also developing the infill materials for CFT. At the moment, because based on the fundamental principles here, we know that these are the characteristics that we want for the best performer of CFT. But based on our discussion just now, you actually notice that there is no one perfect concrete materials that have all the good characteristics for CFT. But you never know what's going to happen in future because nowadays you see a good variety of concrete materials being developed by the researcher. Okay, so I believe one day they might have the ability to work out something that give you a perfect concrete materials for the best performance of CFT. At the moment, there are still pro and cons, plus and minus in between. Other than that, you might want to look into the full-scale testing, which can give you a more representative response, simulating the actual situation instead of the basic one, cylinder testing, small-scale testing. Other than that, I also observed that we have these standard size tube members, which it can be quite handy and is readily available in the market. I foresee probably one day in futures when engineers know more about CFD in terms of their design, it may end up engineers alone, they can freely and they can confidently design like what they design for the conventional columns. We never know, but in this probably is going to be the future trend. Other areas you might want to look into is how do you deal with the joint? How do you improve the bond? How do you maintain the effective confinements over the service life? And also standardness limits. And you have so many combinations to explore and probably the inventions of sustainable infill materials for the CFD. So with that, I come to the conclusions. So far, what we have learned, we learned that the CFT is actually 1 + 1 more than 1. Is taking the advantage of the concrete and taking the complement with the confinement from the tube, it give you a higher axial strength. Okay, and then second one here is CFT. Currently, there have been many being studied, but because you have so many material combinations unexplored, so I see a huge potential in the research in the CFT. And then another one is the behavior of CFT is very strongly influenced by the properties of the materials, regardless the different types of the material. With that, I end my presentations. Thank you for your attentions. And that's it for my presentations and Q&A section.
Well, thank you very much, Dr. Lings. I'm going to read my notes here, several notes that I made during your presentation. First is Dr. Ling discussed the enhanced axial strength and durability of concrete fill tube, or CFT. He outlined its importance and usage in modern constructions, along with how it is both cost-effective in material usage and constructions. He also explained the different types of CFT and materials used to fabricate it. Dr. Ling explained both advantages and drawbacks of concrete materials as well as CFT's stress, strain response, and load properties. Methods to improve CFT's performance were covered, including how to prevent debonding. Dr. Lin concluded his presentation with a discussion on future directions for CFTs and possible challenges and concerns. Right, we go to the next session is question and answer for 15 minutes. Is there any questions? Maybe from the audience here? Yes, we have one here.
Okay, thank you for the opportunity. Good afternoon, sir. It's a very engineering department. Well, it has been done so many concrete material study these days with its own advantage and disadvantage. And also, you explained that about CFT. There are so many material combination that can be used, such as with the steel tube and etc. My question is, do you combination of CFT that use the most these days? That's all. Thank you and good afternoon.
Okay, because the internet line connection is slightly lagging, let me clarify your questions. You are asking about the most common combinations of materials that I personally use or currently the researcher are favor of?
Currently used in industry. So we know that CFT used in like high-rise building, bridge, and etc. And from and also from your study, maybe can you give us the which one is the most advantage from your opinion? Thank you.
Okay, so I try to answer the first part here first. The most commonly used CFT currently is still CFST. That means the tube is made of the steel. And for the high-rise building, this actually in one of the presentation slides, they use a lot of high-strength concrete or high-performance concrete because because dealing with the high-rise buildings, they custom made those tube in the size that they intended to be, and they use high-strength concrete to provide the high air resistance to the members. So currently, the most common one that we encounter at the moment is still CFST with high-strength concrete. Now, those lists of the different types of the materials that I shared just now, I took it from the research, and some there are very extensively studies, such as they also studied FRP, and also only recently now I see some study emerging in terms of the plastic materials. So this is my personal observations from the research field. Now, in terms of my personal studies, because I feel like steel is quite reliable already, they know more on the steel, but I observed that the plastic material, it could be a potential, but you know that plastic material, the performance is actually inferior as compared to the steel and FRP. So if you want to use the plastic materials as the tube, that means you have to work out with something to improve the performance of the infield material. So at the moment, I also try to use this fiber reinforced concrete inside the plastic tube, UPVC or PVC tube, and also my students, master students, use this reinforcement inside. But that kind of reinforcement is not the conventional column reinforcement, just simply steel reinforcement simply one steel bar being embedded inside the CFT lah. So the main reason of doing this is because we want to make the construction process as easy as possible, to make it simple as easy as possible. So in terms of the performance, probably you are curious. At the moment, my personal observation here is for short columns is okay for the plastic tube, and also because the performance is relatively lower, and also but if I use the reinforcement within inside the CFT, slenderness may be an issue. That means when it become more slender, the improvement, the enhancement given by the internal reinforcement, it will be slightly less influential. So this is just a quick summary of what we have found in my studies.
So,
Okay.
thank you, Dr. Lee.
So,
Question for our presenter number 2. We still have about 7 minutes to go. Yes, at the end there.
Thank you for the opportunity. My name is Robert. I'm from the Civil Engineering Department. Good afternoon, sir. Concrete fill tube are widely used in the high under heavy structure, but that is the new for us. So my question is, what the mitigation measure can be applied in the design of the CFD columns to enhance resistance to high temperature and have thus its measure impact cost and also structural efficiency? Thank you.
Okay, let me clarify. You're talking about what are the mitigation measures to increase the impact, is it? Structural efficiency and
Can be
also
applied.
high impact.
Yeah.
Come again? Come
Yeah.
again?
To enhance the resistance to high temperature.
High temperature.
What the mitigation measure can be applied in the design of the CFD? Yeah, high temperature.
High temperature. At the moment, personally, I'm also not sure how they deal with the high temperature. But if you're talking about CFST, they need some coating materials. They need some coating materials that can help to prevent the high temperatures. And I observed there are also studies on the steel structures. What they do some painting over those steel materials. And when being exposed to the high temperature, that kind of painting, I believe there's a lot of micro things there in expand and forming a form like of the protective layer in order to prevent the structures that means to have a direct insulate the structures to have a direct contact to the high temperature. Okay. Now, at the moment, my personal studies still focus more on the strength and the performance. At the moment, I haven't really explored into the durability part and also the temperature issues. Now, my personal observation here is because what we see, if you want to use the columns, CFT as the columns, it is a part of the skeleton frame system. Now, you also another area that you might want to look into, it would be the joint, because just now you asked about the efficiency of the structure, right? So we have to look into the joint also. If the joint is relatively weak, and then no matter how strong you provide the CFT, the structural integrity will not cope up with that as well. So the joint, it will be another issue. Now, in terms of the joint, CFST normally have no issue because they can use the steel technology type of the joint. So the photo shown in the slide as well, also made of steels, and there are two common joints that you can encounter. But how about if you use other material as a tube? For example, if you use plastic material, how do you do the joint part? So I guess this is also another potential areas that if you're interested to study in this field, probably look into how you can provide design a joint. Probably you can even pattern a joint, a design for the joint, so that it can effectively transfer the stress and the moment between the column and the steels. Okay, so this I hope this answers your questions.
Thank you, Dr. Ling. We actually have about another 3 minutes. So if any other participants would like to ask questions, and Dr. Ling is going to give short answer. All right. Is there any other questions? Maybe the online participants would like to ask questions. All right. We have someone who would like to ask the questions. Could you state it briefly?
I would like to ask one question. In the design of CFT columns, how do the differences in the size and thickness of the pipe affect the overall structural performance?
Right, excellent. Dr. Ling, please.
Okay, you're talking about the thickness of the pipe. How do it influence the performance of that? The thickness will leads to the it will influence the confinement effects, because when we talk about you have a thicker tube, that means it is less susceptible to undergo expansions. So that will help to increase the confinement effects and increase the performance of the concrete. At the same time, if you increase the thickness of the pipe, it will give you higher axial strength and lower tendency to undergo linker buckling. So in another way, it's also increased in terms of the performance in the axial resistance. Okay, short answer. I guess this one's okay, huh?
Thank you.
All right. Give big applause to Dr. Ling for great presentation. Thank you very much, Dr. Ling.
Thank you very much. It is my honor to be given opportunity to present here. Good to see you all. Thank you.
Thank you. Now as we go to the next speaker, the third speaker of today, Mr. Hari Darmawan, MSc PhD. Is it Mr. Hari is here, I believe?
Yes, I'm here.
Oh, excellent. I'll read your brief CV because you have a great, excellent CV, so I just have to pick up some of them, okay? Right, Mr. Hari Darmawan, MSc PhD, this dynamic, open-minded, and highly motivated lecturer, received his Doctors of Engineering Technology from KU Leuven, Belgium, and received, until now, he is teaching at National Taiwan University of Science and Technology. Is it correct, Mr. Hari?
Yes, that's correct.
Right. Actually, we are very proud of you. You are able to be one of the lecturers in Taiwan University. Okay. I think you have 45 minutes to have your paper presentations, Mr. Hari.
Yes, sure.
Right. Thank you.
Well, I'm going to share my screen now. Well, I will try it. I was wondering whether the presentation is working now. Just to make sure.
Yes, we can see it clearly and we can hear you perfectly.
Perfect. So, yeah, I will start then. Yeah, well, first of all, good morning to ladies and gentlemen, and also to the students. First of all, I would like to thank Politeknik Negeri Pontianak for organizing this wonderful webinar. And also, I would like to personally thank Ms. Irene Anggreni for inviting me to be a speaker in this webinar. So, in this happy occasion, I would like to present about the self-healing concrete, which can be a future generation of the smart construction material. My name is Heri Harmawan. I'm an assistant professor from National Taiwan University of Science and Technology. So this is the outline of my presentation, starting my short autobiography, introduction, self-healing materials, engineering properties of self-healing concrete, conclusions, and also future perspective. So I will again briefly introduce myself a bit. So I'm Hari Hermawan from Indonesia. Previously, I got my PhD degree from Leuven in Belgium and also Universitat Politecnica de Valencia in Spain. I have obtained also Master of Science degree from National Taiwan University of Science and Technology in Taiwan, and also Bachelor of Engineering from Parahyangan Catholic University in Indonesia. As previously explained by the moderator, I'm currently working as an assistant professor at N2ST, while formerly I worked as a research associate at Leuven for about 3 years, conducting the research about the self-healing concrete. So during my PhD, I involved in the European project so-called Smart Things, and Smart Things stands for self-healing, multifunctional, advanced repair technologies in cementitious system. So this project is funded by the European Commission under the Marie Curie Grant Agreement. And at that time, there were 15 researchers like me, and we worked on the project for about 3 years. The objective of this project is to develop the self-healing concrete technology and also try to apply this in the field, and we hope that we can also penetrate the market with our technologies. So in order to reach this goal, there are many universities and also industrial partners collaborate in this project. So we are in the interface between the R&D, which we were working in the university, and then we go towards the innovation until we hope that we can also penetrate the market with the self-healing technologies. So we mainly work on the durability and the sustainability aspects, structure design, concrete technology, production of the self-healing agents, and also processes and modeling. So I will first introduce about my research. So what is the self-healing? Well, self-healing is derived from our human ability. So imagine if we have a scar or on our human tissue, we can see as it will heal gradually by time. And this is an ability by nature, because in our human body, there is some like DNA that we can help to heal any wounds. So we will try to use like this kind of concept for our human aspect to be applied on the construction material. As we know, concrete is the most consumable material in the world, and concrete can withstand a high compression stress. However, it's relatively weak in tension. And due to the high tensile stresses and also harsh environmental conditions, cracks may occur. And cracks, of course, they may grow from the micro size into the macro size. And due to the ingress of the water and the harmful liquids, concrete degradation may occur. There have been many efforts by many applicators to repair and patch the existing cracks. However, they are costly and also time-consuming. So there is a need to heal a cracks in the sustainable way, and this can be done using the self-healing technologies. Now I will give a bit overview. So you may be wondering, what is the difference between the normal or traditional concrete and the self-healing concrete? So imagine on both of the specimens, we have a crack. And according to the name, because we are talking about the self-healing concrete, you may expect that the crack will be healed. But what's going on with the traditional concrete? Apparently, traditional concrete also possess self-healing ability. But now, what is the difference? The difference lies on the mechanism. On the traditional concrete, it possesses so-called autogenous healing mechanism. And this mechanism is derived from the original components of the concrete. And this component may promote crack healing under favorable environmental condition due to the physical and the mechanical causes. Now, there are five items that we need to consider when we want to talk about the autogenous healing mechanism. The first one, the first factor is so-called clinker content or the cement type, because this will determine the supply of the calcium ions. That's why when we are making a concrete, especially for the self-healing concrete, we have to consider the cement type. Either it's like a Portland cement or like SEM1, or it's like a blast furnace like SEM3. And it depends because with the Portland cement, they have a higher calcium ions than the other secondary cementitious cement. The second factor is the silicate addition. So the silicate addition basically will determine the duration of the healing mechanism. This happens because in many ways we can replace the cement with the secondary cementitious materials, and due to the pozzolanic activity, they will affect the strength development, the setting time, and etc. And eventually, they also will influence the duration of the healing mechanism. The third factor is aggregate. So the aggregate will control the cracking pattern. So normally, we aim for the continuous grading instead of the gap graded, because if the crack are not so good, I think it will be hard to determine their crack width. The fourth factor is the concrete class. So the concrete class determine the healing effect. It's basically also it's related to the strength of the concrete itself. And lastly, it's about the concrete age. So the concrete age determine the healing mechanism. Imagine that the concrete at the young age, they still have a lot of the unhydrated cement particles, while the concrete at the old age or the later age, because the cement have been hydrated, so there will be lower amount of the unhydrated cement particle. And the unhydrated cement particles also will help to induce more hydration and more production of the minerals inside the concrete. So basically, the traditional concrete, it will be divided into three main causes. The first cause is the physical cause due to the swelling. So the material inside the concrete, it can be swell also, and it will lead to the crack closure. With regards to the chemical causes, the crack closure can be due to the continuous hydration and also calcium carbonate formation. While the mechanical causes, it can be due to the broken from the fracture surface inside the crack, and it will lead to the clogging of the cracks due to the particles inside. But what is the most important thing is the autogenous healing mechanism have a limited healing capacity, typically only being able to heal the cracks about 100 up to 100 micrometer in width. Now, the self-healing concrete possesses an autonomous healing mechanism. And this mechanism, it's due to the addition of the healing additives, such as minerals, bacteria, crystalline admixtures, and also their vessels, like capsules, vascular network, shape memory polymers, and etc. So in here, the concept of the self-healing concrete is divided into different area. For the intrinsic, it can be fibers, super absorbent polymers, minerals, and in the section of the capsules, it can be minerals, bacteria polymers. There are also vascular network and also shape memory polymers. But what is the main important here is the autonomous healing mechanisms can easily heal cracks up to 300 micrometer, which is almost like a doubled or tripled from the autogenous healing mechanism. And sometimes it can heal more than 1 millimeter. Now, we move toward into the various self-healing materials. So I will basically start with the slides again, and then we see one by one for each of the material. Now, this is like the use of the fiber. Well, in fact, fiber is not a self-healing agent, but fiber will help us to constrain the crack. So I provide like a short video over here. So you can see here, I have like a specimens and then I crack it with the Brazilian splitting test. And because I put the fiber inside the concrete, so you see when I do the Brazilian splitting test, the concrete did not fail completely, but it's constrained the crack. And with the use of the fiber, we can control the crack width, because when we are working with the self-healing concrete, the most important thing is we have to consider the similar level of the crack width, or we can also make it into a different range of the crack width. Now, the second is the use of the crystalline admixture. Formerly, crystalline admixture was used as a waterproofing agent, but now it transforms into the healing agent. And this is one of the most well-known product from the Penetron company, so-called Penetron Admix. So these crystalline admixtures, if you can see here on the material itself, they are composed of the Portland cement and also proprietary active chemicals. So if you look here, there are some white particles, and these particles are some like active chemicals containing in the crystalline admixture. But the question is how this crystalline admixture works. I will also now run the video. So basically, imagine that if you have a concrete and there is a crack inside the concrete and the water enters the crack. So what's happening? Actually, when the water comes inside the crack, the crystalline mixture will react with the portlandite, calcium ions, aluminum, and the other metal oxide in order to form like millions of the needles inside the crack. And the needles will become an integral part of the matrix, and they will eventually close the crack. So the water could not enter anymore into the crack. And then what's happening if you have another cracks coming on the bottom part? Well, because the crystalline mixture stays dormant in the matrix, so they will again create like crystals inside the concrete in order to block the ingress of the water. So this is the concept of the crystalline admixture. However, how we can incorporate the crystalline mixture in the mix in our mixture, we can simply put it during the mixing stage. But in order to activate the crystalline admixture, the presence of the moisture is important. And also the dosage of the crystalline mixture, especially for this product, is limited between only 0.8 up to 1% by weight of the cement. Because if we use too much crystalline mixture in dosage, there will be an excessive crystallization in the matrix, which later lead to the excessive cracking. Now, I will also talk about the another material, so-called super absorbent polymer. So the super absorbent polymer is actually like it's a chemical product which is containing a copolymer chains. So they are available in the form of the powder. So this is like an image of the dry SAP. How the effect of this SAP, if this SAP gets contact with the water, it will swell a lot, something like this. So what's the concept when we try to incorporate SAP in the concrete? So when water comes inside the crack and we have some SAP in our matrix, they will swell inside the crack and then it will block it with the minerals until the water could not comes inside the crack anymore. However, when the water is not available, this swollen SAP will return back into the original state. So the drawback of using the SAP is the void in our matrix, because if the water is not present, it will lead to such a hollow like this. And if the water comes inside again due to the cracks, and it will be filled again. So it's always like a shrinking and also like swelling effect. Now I will go to the capsule section, which consider the minerals, bacteria, and the polymers. The use of the bacteria is said as one of the most promising self-healing technologies for the production of the self-healing concrete. However, there are a lot of the bacteria that we can use to make the self-healing concrete, and it depends to which MICP pathway. So the bacteria should promote so-called microbial-induced calcite precipitation, or MICP. And this MICP, there are many pathways. So this in the picture on the left-hand side, you can see this is the first pathway, so-called like the metabolic conversion of the organic acid, where they can grow like the calcium carbonate or the minerals on the crack. And it can be also enzymatic urolysis. So this urolysis, because the bacteria, some specific bacteria can produce urea, later it will be decomposed into the carbonate ions, and bacteria will attract the carbonate ions and also take the calcium from the cement in order to produce the calcium carbonate in the crack. These are some frequently used types of the bacteria, such as Bacillus pericus, Bacillus megatherium, Bacillus aureus, Bacillus kochni, and Bacillus subtilis. And you may be wondering, and actually there are many more bacteria, but most of them are in the genus or the family of the Bacillus. But you may be wondering why a lot of researchers use Bacillus type of the bacteria. There are several reasons. First, the Bacillus type bacteria can promote the biomineralization, or MICP, to produce the calcium carbonate. And they are also high alkali tolerant, and they can stay dormant if it's not used, but it can be also be active when they in contact with the water and also the moisture, and they can do the germination inside the concrete. However, the most important thing when we include the bacteria in into the mixture or in the concrete is we need to also include the nutrient, because the nutrient is important for the bacterial growth. Without the nutrient, the cells of the bacteria will die in the matrix, and there will be no production of the minerals. So these are some types or examples of the nutrient. It can be calcium lactate, calcium nitrate, calcium formate, urea, and yeast extract. But it depends also on the compatibility between the bacteria and the nutrient. So this is normally, it has been researched previously by many biologists. This is the example of the commercial product of the bacteria. So this brand, Bacillus, is a company in Netherlands which is producing the bacteria healing agent, and it's basically composed of the polylactic acid particles with embedded bacteria spores, which the type of the Bacillus kochni, organic salts, and also calcium lactate as a nutrient. And the dosage, it's normally between 2 and 4% by weight of the cement. In our project, in the Smart Things project, we also collaborate with the Avecom, the company, to produce 2 types of the biomass agent. So these biomass agents were obtained from the wastewater treatment. The first one is the HTN, which is a bacteria-based agent, and the second is the yeast or the fungi-based agent. However, those agents were are not available yet in the market, and we hope with our advancement and the successful of our project, we can try to promote this worldwidely. The next one is the use of the capsule. And the capsules are differentiated into the microcapsules and also macrocapsules. And the idea when we are introducing the capsules in our concrete matrix is once the crack occurs, the capsules will break and it releases the healing agent into the cracks. So the healing or sealing can take place. This is some of the microcapsules that I work with my colleagues in the project. And it shows, but it has like a different size because this is very small, but this is quite large. When we are producing the capsules, there are also two parameters that we have to take care of. First is the shell, and second is the cargo. The shell, it can be made of the polyurethane, urea formaldehyde, or gelatin or gum Arabic shell. While the cargo, depending on the agent that you want to use for the healing or sealing, it can be sodium silicate, epoxy resin, calcium nitrate, and silane base agent. And normally the size of the microcapsules is between 20 up to 200, while the typical dosage is below 10%. Yeah, this is also some example when I also had a chance to use the microcapsules, and then we include into our mixtures, and later in our concrete specimen, under the UV light, we can see the capsule which are glowing under the UV light because we use like a fluorescent dye in our microcapsules in order to detect the condition of the capsules inside the concrete. The next one, as I mentioned, there is also a macro capsule or macro size capsules. So now we use a bigger size of the capsules, but the capsules are actually made by cutting the tubes, such as like a polymeric capsules here. I also collaborate with colleagues from Italy to make cementitious capsules, and also there are also glass capsules. But you may be wondering how we can integrate these macro capsules in the concrete. So what we can do is in our mold for the beam specimen, we can put like a wire and then we can attach like the capsule one by one on the wire. And especially we only put this in the cover zone of the concrete. So this is an example. I had a specimen on the prismatic and then I do the 3-point bedding test. So since I put the capsules in the cover zone, you can see there is a release of the agent on the bottom line. And this showcase the successful breakage of the capsules during the cracking by releasing the agent into the crack. Now there is also another material so-called like vascular. So vascular network, basically we incorporate like a continuous like a tube or something like a polymeric material. The idea is we can inject the healing agent, let's say from one side here until it come out to the other side. And the idea when the crack appears, especially here in the middle, so the tube, it will break. So when we inject the healing agent from one side, it will heal like this crack area until it can obtain a crack closure. And it can be like a single tube, connected tube, or vascular structure like this. One of my colleague in Belgium, they make a 3D printed network such as like this, and they did a demonstration project by fabricating the concrete walls, and they already also put the vascular network inside the concrete, and when the crack happens, they inject the healing agent from this tube, and then you can see here there is like a leaking of the agent via the crack. So it means like the tube is already broken inside due to the cracking. And lastly is the shape memory polymers. So the shape memory polymers, basically it's like a chemical, like a product or the polymeric material where it can remember their original position. So imagine for instance here on your structure, and if it has a cut, because the polymer itself can remember their own like original state, so it can heal by themselves. So this is also the same concept with the self-healing technologies. Now I will move to the engineering properties of the self-healing concrete, which is very interesting. Now, during my early time of my PhD, I had a chance to use these two products, penetron admix for the crystalline admixture, and also bacillus bacteria for the bacteria. And then I use only the optimum amount as suggested by the producer, 1% crystalline admixture and 2% of the bacteria. And then I made a specimen and then I cracked the cylindrical specimen at 7 days old via the Brazilian spitting test. And how we can measure the crack width. So basically, imagine on your crack specimen, you can put some marks. I put here like 3 white marks. And then on each mark, I used optical microscopy, and then we can check like the width of the crack. So there are like 3 spots in this case. This is the example of the picture of the crack at 0 day, which is after cracking. And it's logical because there are no formation of the minerals because it's just under cracking. And then we subjected the crack specimen into the healing condition, which is water submersion. And then we will mimic the effect between the short healing versus the long healing. So what will be the difference? After 21 days underwater submersion, which is I said as a short healing, you can see there is already like a limited crack closure with a low precipitation of the healing products. So you can compare between the 0 day and the 21 days. And then what's going on with the long healing time? So with the long healing period, in here, I set 121 days. We can see there was already like a full crack closure with the high precipitation of the healing product. So this showcase like the evidence of the self-healing phenomena. However, there are some also behavior of the crack closure. So here I put some examples. If the crack cut the partition between aggregate and the aggregate, after a short healing, you can see there was nothing on the crack mouth and also inside here. But after a long healing, it's already completely filled with the minerals. However, since the aggregate do not contain the healing agent, they will not promote the crack closure, but this crack closure is due to the production of the minerals from the inner part of the crack, and they will coming out to the top. So that's why this will be healed due to the mortar section. And then you can see here, if the crack cut the partition between the mortar and the mortar, and since the mortar containing the healing agent, you can see on the crack mouth, there are already some minerals forming. And with the longer healing time, it will be eventually closed. The same way, if it cut the partition between aggregate and the mortar, on the mortar side, it will have a lot of the crystals here, and then it will eventually close the crack after a long healing time. So this is like the difference behavior when they cut the partition of the mineral aggregate or the mortar. Now this is the result. On the x-axis is the initial crack width. On the y-axis is the final crack width. On the reference specimen without the healing agent, you can see there are some distances between the crack either were not fully healed and the crack are fully healed. But most of the portion, the crack were not fully healed because they do not contain any healing agent. But what's happening if we try to include the crystalline mixture and bacteria, you can see all the points which were originally here, they will go downward. It means there is like a progressive of the crack closure. Although they are not fully closed because it's only a short healing time, 21 days. And after 121 days, which is I regard it as a long healing time, all the portion of the crack are already fully healed. While only a few points, they were not fully healed. How to quantify the healing efficiency? We can use this formula by considering the final crack and the initial crack width. And this is the result. There is like a proof that when we include the crystalline mixture and the bacteria, they will increase the healing efficiency either after a short healing or after a long healing. We can also characterize the healing product because some of the healing products will come out from the crack mouth, and then at that time I scrap the minerals, and then I do the test with the FTIR in order to check the spectrum of the wave number. And if you learn about the mineralogical analysis, this specific spectrum, like the numbers I presented here, they are belong to the calcium carbonates in the polymorph of aragonite. Now, we already know that the self-healing phenomena, it's evident. However, when we produce the self-healing concrete in the lab, normally it's unconfined. But when we want to apply this in the field, of course, we will be dealing with the reinforcement and also our concrete mixtures. So you may be wondering, is the self-healing effect it's efficient to close the crack, or may it also contribute to the bone recovery? To answer this question, I designed like a pull-out specimens like this, where I only subjected to the half of the embedded region, which is like a 5 dB, and then I fabricated like 5 different mixtures, reference without any healing agent, concrete with the bacterial biomass, concrete with the fungal biomass, concrete with the grease mixture, and the concrete with the bacteria. And then I designed like a specific pull-out test for a self-healing assessment by we try to pull out the concrete from the reinforcement, such as like this. Then from this test, we can have a lot of information about the ultimate bone strength, mean bone strength, fracture energy, and also the slip. But especially in this presentation, I will limit myself into the ultimate bone strength. This is the result of the effect of the various healing agents on the mechanical properties. On the left-hand side, you can see at 28 days, the compressive strength of the reference reached 47 MPa. And with the addition of the healing agent, they did not induce negative effect, but they even slightly increased the compressive strength. On the right-hand side, which is very interesting, the ultimate bone strength of the reference reached 14 MPa, but the addition of the healing agent significantly increased the ultimate bone strength, especially on the use of the Ca, crystalline mixture, and also bacteria. But to answer this question, we can go to the microstructure of our concrete mixture. So here you see the microstructure of the reference concrete is actually amorphous, which is quite similar to the HDN and the yeast. But the thing is, when we include the crystalline mixture and bacteria, there was a massive production of the calcium needle in the matrix. And this will help to improve the strength and also have a good packing. Also, we found on the reference specimen, since there are some voids happening inside the matrix, and with the C and the BAC, the voids were filled with the calcium, with the crystals inside. And this proved that the strength it's improved by the addition of those specific agents. Now, in order to assess the self-healing effects towards the bonding, I tried to crack the specimen with a different crack width between 200 up to 500. And we found that the ultimate bond strength drastically reduced up to 60, between 60 and 80%. And we tried to heal the specimens underwater for 28 and 112 days. And we can see some proof. So after healing for 28 days underwater, we can see there was like a little like white precipitation happening on the crack mouth for all of the specimen. But especially on the use of the C and the BAC, there are some healing products coming out from the crack, and we normally call this as a stalactites. So there are some stalactites on the C and the BAC. What is more interesting, after a long healing time, 112 days, there are a massive production of the healing products coming out from the crack for all of the healing agents. While on the reference, it stays like a granular structure on the crack mouth, and it's very different with the other healing agent. And we also have identified this product as a calcium carbonate in the polymorph of calcite or aragonite. The most important thing here, there was a bone restoration after the healing, because I previously mentioned that there was a reduction of the ultimate bond strength up to 80%, but with the healing time, there was a limited bond restoration. However, it's only valid after 28 days, while above 28 days, it will stay constant. And you can see here also during the test, the crack is still closed, but after the test, the crack is reopening again. It means the healing product were not strong enough to sustain the higher stress. Now I will move to another material, the microcapsules that I previously mentioned. So at the time, I had a chance to use this product where the microcapsules is composed of the polyurethane as a shell, and the inside the cargo is the water repellent agent with the mean diameter 59 and 88 micrometer. To start, I did the preliminary investigation by making several mixtures on the reference mixtures, and also I include 0.5, 1, and 1.5% microcapsules with the size of the 59 micrometer. And also I include the 1.5% microcapsules with the size of 88%. So what are the results from the fresh test, especially on the slump? The addition of the microcapsules did not considerably affect the slump, because here, although the reference has a slump of 180, it's only different by 10 or 20 millimeter, but they are still classified as an S4. With regards to the air content, the addition of the microcapsules increased the air content of the fresh mix by more or less 1.2%. On the fresh density, the addition of the microcapsule did not influence the fresh density. However, the most important part is about the strength of the concrete. However, I should mention that the addition of the microcapsules is significantly reducing the concrete strength. So for instance, the addition of the 0.5% will reduce 21%, 1% 37%, and 1.5% will reduce 44% of the strength. And this is also evident on the tensile spreading strength. But there is a way in order to optimize the concrete mix design for the microcapsules that I have been published previously in another journal. So we will go forward to the self-sealing test. So basically, for the prismatic specimen, we crack it and then we put the epoxy on the bottom part of the specimens. And then we only still keep like the crack area in order to be submerged, in order the specimen to be submerged into the water. So we do this capillary water absorption test with a different time in order to assess their sealing efficiency. So this is like the result of the water uptake versus the time. We can see on the reference specimen with the crack condition on the blue line, the water ingress rapidly via the crack. However, on the use of the microcapsules, there was a very limited water ingress due to the effect of the microcapsules. And then this is quite similar to the reference with the uncracked condition. And if we calculate the sorption coefficient, and then we can also calculate the sealing efficiency based on this formula. And we can confirm that the addition of the microcapsules can increase the sealing efficiency up to close to 90%. And this is the picture, the difference between the reference concrete and the microcapsule concrete. You can see, because the water can penetrate rapidly into the crack on the reference concrete, but with the use of the microcapsules, we cannot see any sign of the water ingress here. That's why the result that I presently showed before, there was a very limited water ingress. Now, let's have a look what's happening inside the crack. So actually, when we look into the microstructure via SEM, a lot of capsules have ruptured on the crack zone. It means the sealing agent have been released from the capsules and they covered the crack portion. This is also the evidence when we do the compression test. We can see there were some wet spots on the surface. And if we look into the SEM, due to the high compression stress, the capsules break and they release the sealing agent into the crack. That's why we can see a lot of white or wet spots in the surface. I also had a study about the bond between the capsules and the concrete matrix, and interestingly, on the outer shell of the capsules, the cement hydration products can appear. So
Mr. Hari, 10 more
yes,
minutes.
yeah. So this is a cement hydration product from the etching guide, and also there are some Portlandite, and it's very interesting because capsules are very compatible with the concrete matrix. Lastly, I will talk about the cementitious long capsule. So as I mentioned, the capsules are quite big, and at the time I had the chance to use this as provided by my colleague from Politecnico di Torino. So basically, I make a concrete where I replace the coarse aggregate with the capsules, because the capsules geometrically they are quite resembles to the coarse aggregate. But before we include to the concrete, we also try to assess the survivability of the capsules with the different mixer. So there are tilting drum mixer and also planetary mixer. How to do this? We make a mixture, and then we add the capsules with a certain number of capsules, and then we mix it again. Then we place the fresh mix in onto the sieve. Then we remove the fresh mortar from aggregates and the capsules. And finally, we can count back the number of the intact and broken capsules. From our result, it shows that the capsules are 100% survive during mixing inside the drum mixer, but some capsules were broken in the planetary mixer. It's logical because the planetary mixer will exert a higher stress and higher impact as compared with the drum mixer. So this is also, I try to make the specimens by incorporating the capsules into the mixer, and then I make the cube specimens and the cylindrical specimen for the testing. In addition to that, I also fabricated the capsule-based prismatic specimen. And how to do this? And we put like one layer of the concrete, and then we put 3 capsules in the middle part, and then again another layer with another 3 capsules until we fully fill the mold. And according to the result on the fresh properties, the slump decreased from 130 until 100 millimeter, but this is not very significant. And also the air content increased from 3% to 4% by the addition of the capsules. And this is due to the disturbance of the packing of the concrete materials, because the capsules, as I mentioned, they are quite relatively big in size. With regards to the hardened properties, in fact, the addition of the capsules reduced the strength by 8%. This is because the capsules were regarded as a weak spots in the matrix, while in terms of the tensile splitting strength and also ultrasonic pulse velocity, they remain constant. So this is some proof when we did the compression test, we can see the capsules inside broke and it released the sealing agent to many cracks. While on the 3-point bending test, as this figure have been shown previously, this is some proof of the successful capsule breakage during the testing. I also did the self-sealing properties as I formerly did for the microcapsules, and then we found that the sealing efficiency reached 75%. So for the conclusion, cracks are naturally unavoidable in many concrete structures. And then this can be mitigated by using the self-filling materials and to produce the self-filling concrete. And in addition to this presentation, there are many more publications also mentioning that the crack healing, it's very evident. The aim of using the self-filling material, we will try to promote the durability protection, and also we will try to prolong the service life of the structure, because this means we will go forward the sustainability in order to reduce the carbon footprint. However, I should also stress that knowledge on concrete mix design is very important, and optimizing the concrete performance is the key. Because as I showcase for some self-healing materials, not all healing agent induce positive effect on the concrete. So we need some optimization in order to get a better performance. My future perspective will be, well, I found one of the review paper. This is about the number of the original research article about the self-healing concrete. So now it's growing very steadily. And well, now because it's only limited until 2022, but I pretty believe that the publication about the self-healing concrete will be more than this number. And then this is also a bit geographically number of research article about the self-healing concrete. I should mention that many countries such as China, America, Belgium, and Netherlands, they produce a lot of the articles about the self-healing concrete. However, there is there is like a low amount of the paper from our country, from Indonesia. So I really strongly suggest to the lecturer, researchers, and students in Indonesia, if you have a chance to work with the self-healing concrete, please do, and then try your best to also check the articles and then how the healing mechanism works. So we will have more publication from our mother country. So I would promote about the advancement development of the self-healing concrete in Indonesia by using, for example, local material or a bio-based material, secondary cementitious materials, chemical additives, creation of the patentable self-healing materials. And also, we will try to promote the surface life of the structure, increasing the durability and improve healing, that we hope that we can revolutionize the construction in Indonesia. So if you want know more about the self-healing concrete, I do have a review paper which you can freely download in the internet in the journal Processes to get a better understanding about the first concept. And
Mr. Hari, 3 more minutes.
Yeah, and I still have also a lot of publication about the self-healing concrete that you can search in the either Google Scholar or in the Science Direct, and please find it. That's all from my side, and thank you for your attention. It has been my honor to be here with you all.
Well, thank you very much, Dr. Hari. I would like to outline several points. Dr. Hari Hemawan outlined the principle behind self-healing concrete and the various methodologies with which concrete can be healed when cracked, including autonomous mechanisms that heal cracks. He also explained how healing occurs and the time frames required to bring about complete healing of cracks, along with the various healing agents and the effectiveness as healing agents. By healing the concrete, the bond properties within the concrete are restored, thereby optimizing the performance of the concrete. The next will be question and answer. Audience, please, if you have any questions, yes.
Bismillahirrahmanirrahim. Mr. Hari, thank you for your presentation. It's very good for me. Let me make a lot of knowledge. I have 2 questions for you. I'm sorry, my name is Susi Haryani. I'm from the Department of Civil Engineering, Politeknik Negeri Pontianak. I have 2 questions for you. First question, has this self-healing concrete been applied to aggressive environmental conditions such as sea water? And the second question, how to get the self-healing agent? Thank you, sir.
Okay, so thank you for your question. I will recall back about your first question. So your first question, whether the self-healing concrete has been applied to the aggressive environmental condition, the answer is yes. Because actually in our project, we were assigned to different topics. For myself, I personally work on the optimization of the self-healing concrete mix design. Well, other colleagues, they work on the durability part. So they also subjected to the harsh environment, like a high pH, like a salt water, and also like a freeze and thaw, and they work best with the self-healing concrete. But the thing is, we have to get the healing mechanism faster if it is subjected to the harsh environment. That's why we have to use like the optimization of the mix design in order to let the concrete or the healing agent can grow like the massive production of the healing products before the aggressive environment that will lead to the deterioration of the crack happens. So this is one of the way. And I think regarding your second question, you ask about how to get the self-healing material. Is it correct?
The agent. Yes, the agent.
Yes. Well, for the self-healing agent, unfortunately, I do not have an access in Indonesia, whether we do have a channel or not, but I do have some connection with my colleagues because in Europe, there are some companies who are producing the healing agent. So the first one, as I previously mentioned in my PPT, there is a company so-called Penetron. So this company actually is based in USA, but they have a big branch in the Italy, and they make a lot of the crystalline admixture. And I just remember that we do have also a Penetron Indonesia. Maybe if you want to work with this healing agent, please try to get contact information about the person in charge from the Penetron Indonesia and get the samples, because at the time when I was doing a PhD, I also asked to the company to send like a big bucket of the crystalline mixture, and also we only use 1% by weight of the cement, which is not a lot and it's not so costly. And with the bacteria, yeah, a company in Netherlands, they already produce like a so-called like a basilisk bacterial agent, and they have like their own technologies to do this. I personally did not make my own product, but I used the commercial product in order to prove whether the self-healing mechanism it's evident or not. But with the using of the bacteria, I think you can also work with the biologist or the chemist in order to integrate the bacteria into the concrete, because if we try to take the bacteria from the soil, let's say, or from the other resource, we have to ensure they should stay alive during the lifetime. Then to do this, we have to move to other several techniques. For instance, with the use of the bacillus that I use, remember that the bacteria we did not include directly into the concrete, but we impregnated into the polylactic acid particle. This is to increase the viability of the bacteria, because we need to ensure the bacteria stay alive and stay dormant in the concrete. So if you have like some certain products, let's say like bacteria in the liquid solution, I think one of the way in order to get this or make sure the bacteria stay alive, we try to encapsulate it into the capsules or we impregnate it into the aggregates. So this is some of the ways in order to make sure that the bacteria can work best with the concrete environment. But normally, like a bacillus type bacteria, since they are high alkali tolerant, they can survive in the harsh environment of the concrete. So I think, as I mentioned, I'm very sorry that I could not have an answer for some self-healing agents available in Indonesia, but I think, yeah, it needs more research. And I have also a connection with my friend in the Politeknik Negeri Malang. I think one of the researchers there, they already make like a self-healing concrete with the bacteria. So maybe you have to search for it first.
Okay, thank you, sir.
Right. Thank you. Audience, any other questions? Yes.
So, good morning. My name is Tania Dia Ayuni, a final year student of Civil Engineering Department. Well, I actually have two questions. The first one is, if we use the self-healing concrete, could it decrease the possibility of earthquake-resistant building collapse or break? And the second question is about could the brick, self-healing brick, holds water pressures in the dam or tunnel buildings and could increase the resistance rather than using the regular bricks? Thank you.
Yes, thank you for your question. It's very interesting. Well, to answer your first question, whether the self-healing concrete can resist to the earthquake forces, I would say it's very difficult because when we are working with the self-healing concrete, as I mentioned, we try to limit the crack width, let's say between 100 up to 300 micrometer. So this is the typical crack width that we are working on, because the aim is we imagine like the crack happens in the slow progressive. So while with the earthquake, I think the force is too sudden, and then they will exert a very dramatic force, and it will lead to a very big of the crack. And I would suggest that if you are working with the self-healing concrete in relation to the earthquake, I think it will not match, because the self-healing concrete, they cannot heal the crack with a very big crack like 5 centimeter. It's nearly impossible because it needs like many years to produce the calcium carbonate in the crack. So I think the application of the self-healing concrete, normally we can apply it into the structure like a utility building, like a dam or a water tank, bridge, something like a utility building. And it's not also applicable on the buildings. You can already imagine, because self-healing concrete, they needs moisture and water for the activation. But for some of the buildings, if we use self-healing concrete and then we already put like a facade on the outer on the outer surface, and there will be no moisture or water can enter that one. So I think it will be very costly, and also it's not so effective. So what I would mention is it depends on the function of your building. We can use the self-healing concrete, but they cannot resist to the earthquake, because as I mentioned also on the bone strength, when I do the bone test, the crack will be reopened again, because the healing product, they were not very strong to restrain this stress. And to answer of your second question, of course, with the dam, I have also some knowledge about this. So some colleagues in the Netherlands, they really use the bacteria healing agent for the dam, because imagine that the dam, there is like a water on the dam structure, and since like the water always get contacts with the crack, so like there will be like a production of the healing products in the concrete with the crack. So it will really stop like the water ingress, and they will resist to the water force on the dam. So this is quite applicable for the dam structure. Also, there are some like a proof of concept about this, and I think you will find more if you read some papers in some publications. I hope I answer your question. If not, you can ask more.
Yes, that answered my question. Thank you so much.
All right, thank
You're
you.
welcome.
And the last ones at the end. That's
Good afternoon, Mr. Harry. First, let me introduce myself. Taufik Habibillah from Department Civil. My name is Taufik Habibillah from Department Civil Engineering in Polyteknik Stage of Pontianak. Here my question is any other chance this self-healing concrete can be applied on pavement, or more specifically rigid pavement? If this self-healing concrete can be applied on rigid pavement, what is the benefit of this material on rigid pavement? Thank you.
Yes, thank you for your question. Well, personally, I do not have so much experience like working on the pavement, but I do know like there are some researchers who are working with the self-healing concrete with the pavement, because I think the pavement that you mean here is like for the application on the road or the highway, while we do not use, or we can combine also like the asphalt with the self-healing concrete. And there are some research about this, and they prove also, because on the road there will be like some impact due to the vehicles and etc. But the thing is, they can also absorb like the CO2 and also the water into the concrete pavement. Then with the use of the self-healing concrete, like the cracking on the road, it can be healed also with the self-healing technologies. But as I mentioned, I do not have so much a lot of experience on the pavement, but I do believe that the self-healing concrete can be also applied in this structure.
All right, thank you, Mr. Ray. I think that's it.
Thank you very much.
Hello? Yeah. Right, thank you. Yes, maybe we still have a yes, one more. All right, one more. Make it short. All right, one more. Ibu Puspita.
Thank you for the opportunity. Good afternoon, sir. It's a fascinating explanation from you. My name is Puspita from Civil Engineering Department. I'm wondering about self-healing methods from bacteria. I'm wondering, just like the yeast we common use in our bread dough, it's vulnerable to damage if it's not stored and or maintained properly. So that in time when we want to use it, it won't work. Okay. I mean, there are living beings in whether it's still dormant or dead before we use it. The question is how to keep the bacteria dormant while during testing everything were kept in ideal situation. Yes, we can keep them dormant before the put into our concrete, but how do we keep them dormant? Like for example, our concrete is still okay for years. It exposed to the weather all day, hot and cold, rainy, and etc. Then suddenly it cracked years later. And by that time, how do we know the bacteria still can keep the concrete heal? Well, that's the first question. The second question is from the study you did in self-healing concrete, does it fully heal with full strength or the concrete decrease in strength? Thank you.
Yeah, so thank you very much for your questions. I think it's very critical. And to answer your first question, how to ensure the bacteria alive, as I previously mentioned from the other audience, I told you that in order to make the bacteria stay alive and stay dormant, we have to impregnate the bacteria into vessels, as I mentioned, like our capsules or the aggregate. And then once it's cracked, how we know that it's still active or how the bacteria did not or die, let's say, we can use like test so-called, I'm not sure do you know or not, it's so-called flow cytometry. So with this flow cytometry, we can take the extract of our concrete matrix, and then we crush it. Then we do this test with this flow cytometry in order to know how many cells of the bacteria live and how many cells of bacteria died. And we can also do this. But one of the research from my colleague in Netherlands, they even have like a concrete structure with the age of the 10 years, and the bacteria still show the germination. Because remember, when they are in the vegetative cells, they will produce like a bacteria spores, and the bacteria spores, via the sporulation, they will make a spores, and the spores will return back into a vegetative cells via germination. So it's like a cyclus, like a circle cyclus. It always be growing for the bacteria. So I think one of the way we have to impregnated them in order to make sure that it's viable. The second question, which is also very interesting, when the concrete is cracked and let's say we also do again the compressive strength, actually there is like a little mechanical recovery. But when we want to prove this, we should not let the concrete like fully fail during compression test, but we can do like maybe only 60 up to 70% of the compressive strength, and then let them heal underwater. And then we do this again, and there are some research showcasing that the compressive strength can exceed the original one or the ultimate strength. So it's very promising because the minerals that we are growing in the self-healing carpet is a calcium carbonate. And calcium carbonate is basically one of the cement hydration product. So this will help hand in hand in order to enhance the mechanical performance. I hope this answer your questions. You're welcome.
That's sorry, we have a bit of issue with our microphone today. So give big applause to Mr. Hari Darmawan, PSC. That was a very insightful presentation. Thank you, Mr. Hari Darmawan. All right, ladies and gentlemen, seems that we can going to continue with our four speakers. Mrs. Lee Mariani, SDM Engineering. Mrs. Lely?
Yes, I'm here,
Hello? Hello?
Oh, yes, ma'am, I'm here.
Miss Lely.
Hello.
The audio is clear?
Hello, ma'am.
All right.
Is it clear enough, my voice?
Yes, we could hear you, but it seems there's a bit of more feedbacks on your audio.
Okay, what about now?
We cannot clearly hear from the Miss Lily.
Hello, ma'am.
Okay. Right.
Hello, ma'am.
Okay, Mrs. Lely, let me read your brief CV. Ms. Lely Marini is one of lecturers at Civil Engineering Department of Pontianak State Polytechnic. She completed her master's study at University of Malaysia, Sarawak, and she currently is in her final years of PhD programs at University of Malaysia, Sarawak. So, Mrs. Lily, we expect a new PhD lecturer coming next year.
Amin, amin, inshallah.
Right, okay. Miss Lily, please, the time is yours for 45 minutes. Time is yours.
Okay, thank you, ma'am. Okay, I will share my presentation first. Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon and warm greetings to everyone. First and foremost, let us offer our praise and gratitude to Allah Subhanahu wa Ta'ala, as it is by His grace that we are able to gather here in good health. I would like to extend my deepest appreciation to Politeknik Negeri Pontianak, particularly to the Director, Dr. Haji Widodo, PSSTN PMCE, representing and his team, to the head of the Civil Engineering and Planning Department, Mrs. Insinyur Hajah Eti Rabi Hati MT, and to the seminar organizing committee, led by Mrs. Irene Anggraini, ST MSc, and her entire team for giving me this valuable opportunity to contribute to this event. My gratitude also goes to the previous speakers who enthusiastically share the latest information in the field of civil engineering. May this be a source of blessing for us all. Amen. I also wish to thank our host, Mrs. Nurul F. MED, PhD. How are you, ma'am? Hopefully you can find well now. Thank you and warm greetings. Now to proceed with today's seminar, I ask the final speaker will share some insight on the topic Advanced Technology in Sustainable Civil Engineering Infrastructure under the title Mechanical Performance of Steel Fiber Reinforced Ultra High Strength Geopolymer Concrete. I hope everyone remains enthusiastic until the end of the session. Discussing advanced technology in sustainable civil engineering infrastructure is crucial because new technology enable the development of infrastructure that is more environmentally friendly, efficient, and durable. This innovation supports carbon footprint reduction by shifting from conventional material with high environmental impact such as Portland cement to alternatives like geopolymer concrete, which significantly decreases carbon emission. Why? Because geopolymer concrete no using cement at all. In this context, the choice of the title Mechanical Performance of Steel Fiber Reinforced Ultra High Strength Geopolymer Concrete is highly appropriate, as ultra high strength geopolymer concrete reinforced with steel fibers offers a solution that support sustainability while enhancing the mechanical performance of infrastructure. Using geopolymer concrete reduces carbon emission, aligning with global efforts to minimize the environmental impact to the construction sector. Additionally, steel fiber reinforcement increases durability against dynamic loads and reduces the risk of cracking, making it an excellent material for projects that require long-term durability and efficiency. This title reflects the importance of research on the mechanical and sustainable aspect of geopolymer concrete, integrating resilience and innovation that are highly relevant to the future infrastructure technology. Okay, for this slide 2, let's take a look at the following image. Here, I intentionally use AI to understand its perspective on modern infrastructure, and here are the results. Amazing. So, then what about us? AI is everywhere today, and we can avoid it. However, as humans, we need to adapt and live alongside it. We should be wiser as we are a creation of Allah Almighty Subhanahu wa Ta'ala. This is a challenge we need to face with optimism. So it's not about AI taking over. Now back to the image. See the tall buildings created here, strong, organized, dynamic, beautiful, and green. Main challenge in modern infrastructure. One of the primary challenges in modern infrastructure is the increasing need for structures that are strong, durable, and environmentally friendly. With rapid population growth and urbanization, infrastructure must not only meet functional and aesthetic requirements, but also support environmental sustainability. Eco-friendly infrastructure emphasizes the use of low-carbon materials and technology with a focus on longevity and minimizing depletion of natural resources. This demands encourage engineers and research to seek sustainable building material alternatives such as geopolymer concrete, which reduce dependence on carbon cement and minimize negative environmental impacts. Okay. For the slide 4, this is I will show the problem and challenge. For the first of all is OPC production process. Why OPC production process is our problem and challenge in here? Okay. Rapid urbanization is boosting construction, especially for concrete structure. But using so much cement in construction has major environmental impacts. Cement production is a top contributor to CO2 emission globally. You see this one, the image. This is how the hazards or the harm for the OPC production process. Responsible CO2 emission CO2 and nearly 2% of all energy used worldwide. This high not only increases carbon emission, but also affects social needs, producing ordinary potland. This one, OPC plant causes environmental problem.
Dibereskannya aku berasa bekerja tidak becus.
Okay, and then around 65 until 75% of the total greenhouse gases linked to the concrete and requires a large amount of raw materials. It takes around 2.75 tons of materials like limestone, shell, and silica to make just 1 ton of OPC. So let's make it clear. For 1 ton OPC, we have to spend all this many damage from here. Additionally, the cement industry uses up 1 trillion liters of water per year, and each ton of OPC needs 115 until 125 kilowatt hours of energy, making it one of the most energy-intensive building materials, only behind aluminum and steel. The environmental impact of OPC of production goes beyond emission and research use. Its production process speeds up climate change and harms ecosystem due to high energy demands, extensive mining, and pollution. This effect has led many countries to create stricter rules on carbon emission. Still, OPC remains the most widely used binder in construction, worsening climate change and increasing extreme weather. Switching to alternative materials such as local material or industrial byproducts can help reduce this effect. Using less material in concrete production allows us to lessen our dependence on OPC without losing the durability and strength of traditional concrete. This change would be a major step toward more sustainable construction, helping to save resources and reduce the environmental impact of the construction industry. For slide 5, this is from my paper. Oops, sorry, okay. In my technical review paper, titled An Analysis of the Environmental Effect of 3 Types of Concrete, highlights some ways to lower embodied energy in concrete while maintaining high strength. I discussed various strategies for creating concrete with low embodied energy, EE, value, and high compressive strength. One primary approach involves selecting raw materials with low carbon footprints and minimal processing energy, including the use of eco-friendly additives and reducing traditional Portland cement in favor of more energy-efficient alternatives. Another key strategy is enhancing compressive strength by optimizing concrete mixture with low EE ingredients. Adding pozzolanic materials like fly ash, slag, or silica fume can lower cement requirements and thus reduce EE. Additionally, adopting energy-efficient production methods such as advanced mixing techniques or renewable energy research significantly decrease the environmental impact. techniques like energy efficient drying and curing, as well as reusing heat from other processes, can further reduce energy consumption. Conducting regular energy audits throughout production is essential to continuously improve efficiently without sacrificing concrete quality. Considering this approach allows for achieving balance between low EE and high compressive strength. However, no single type of concrete can universally be labeled as the best. The choice depends on the specific requirement of a project, factoring in cost, energy efficiency, compressive strength, and environmental impact. Among the types evaluated, geopolymer concrete emerges as a promising option due to its generally lower EE value compared to ready-mix concrete RNC and reactive powder concrete RPC. You can see from this graphic. For the yellow one is ready mix, and the green one is for the RPC, reactive powder concrete, and the brown one is geopolymer. So geopolymer is making alternative solution or best option for this to reducing EE volume. Studies suggest that using alternative additives like slag and fly ash can reduce EE while maintaining adequate strength. Nonetheless, careful evaluation of each concrete type and project specific is crucial before making a final selection. Besides that, I make comparison also with embodied carbon. The data show that different types of concrete come with traits of between strength and environmental impact. While some mix balance, but higher strength usually means more environmental costs. So reactive powder concrete (RPC) has the highest strength, followed by ready-mix RMC and geopolymer concrete, making RPC and geopolymer concrete good choice for projects needing extra strong materials. However, RMC often has the lowest environmental impact, and geopolymer concrete tends to be more eco-friendly than RPC while still offering high strength. If you see this from the diagram, and you can compare the RMC and the geopolymer, there is become more eco-friendly than RPC. In summary, choosing between RMC, RPC, and geopolymer concrete depends on the specific needs of the project. For projects that need moderate to high strength and prioritize sustainability, RMC could be the best choice. For extremely high strength, both RPC and geopolymer concrete are good options. So the geopolymer concrete may have a lower environmental impact than RPC. So there is a which the project that we want to make for the concrete. You can choose RMC, you can choose RPC, and geopolymer depend on your project. Okay, we see the next slide. We go to forward, please. And the second problem and challenge this side of OPC production process, that is byproduct. Manufacturing and construction generate byproducts like fly ash, like silica fume, metakaolin, and red mud, each with specific hazard that need careful handling to protect human health and the environment. Like fly ash. This one fly ash. This one is a byproduct of coal combustion containing heavy metals that can pollute air and soil if not properly contained. And then slag produced from metal smelting may contain toxin and should be safely stored to prevent contamination. And other example, there is silica fume, fine particles that, if inhaled, can cause respiratory issues like silicosis, so protective measures are essential. So other material that can we have to focusing how to make it safe for our environmental, especially for human. In summary, this material can be used in industry but requires safe storage protective equipment, and emission control to prevent environmental health risks, particularly to exposed workers. Okay. And then the third problem and challenge, that is cracked concrete. Cracked concrete, or another challenge, lies in the limitation of conventional concrete to withstand extreme environmental conditions and increased load demands. Traditional concrete, widely used in construction, often struggles to maintain durability under high temperature, harsh weather, or corrosive environment, with growing urban infrastructure needs, heavier loads from traffic, and larger structural demands. Conventional concrete may not provide the strength or long-term durability required to ensure stability. This can lead to faster cracking and damage under high-performance conditions. Consequently, there is a rising need for advanced materials with superior mechanical performance, enhanced durability, and resistance to harsh environmental conditions. Materials such as ultra-high-strength concrete reinforced with steel fibers offer improved resilience and can better withstand this demanding condition. Okay, so the solution is, for me, is geopolymer concrete. Geopolymer concrete is an eco-friendly solution to industrial waste problems because it can use byproducts like fly ash, slag, and metapolyene, and etc. Here are its benefits. First, use of industrial waste. Reduce waste by using industrial byproduct as raw materials. Second is lower carbon emission because producing geopolymer concrete reduces less CO2 than traditional cement because the geopolymer concrete not using cement. And the durability. Geopolymer concrete is more resistant to chemicals, corrosion, and sulfur attacks. And after that, reduce pollution. Help reduce air and soil pollution by recycling industrial waste. And strength and the durability, it has high compressive strength and can be reinforced with steel fiber for structural use. And lastly is energy efficient, requires less energy in production compared to regular concrete. Because how to make the geopolymer concrete, we can use the ambient temperature. So just waiting for the geopolymer concrete is bonding each other inside the concrete. So that is after that we can get the strength from that. Okay, this slide is talking about the history of geopolymer concrete development. The development of geopolymer concrete began as an effort to create an eco-friendly alternative to Portland cement, which has high CO2 emission. Here's a brief overview. In the 1970s, Professor Joseph Davidovich, a French scientist, first developed the concept of geopolymer, a process using industrial waste like fly ash and slag mixed with alkaline solution to create a strong, durable material. In the 1980s and in 1990, the concept of geopolymer began to attract attention in academia and industry. Universities started exploring geopolymers' chemical and mechanical properties, tough high costs, and limited understanding slow widespread use. In the early 2000s, research on geopolymer concrete grew significantly, especially with the increasing focus on the environmental impact of construction industry. Research, especially in Australia, highlighted geopolymer concrete's high strength and durability. The first small-scale infrastructure project using it were launched. In the 2010s, more countries introduced stringent regulation on carbon emission reduction, leading to increased consideration of geopolymer concrete as a green alternative. With rising environmental awareness, companies began large-scale production. New curing methods and standard made polymer concrete easier to use. And now, 2020 innovation and application, geopolymer concrete is now used widely in infrastructure projects. Innovation like steel fiber reinforcement and AI-driven mix design have improved performance, supporting sustainable construction. What are the components inside in the geopolymer concrete? Okay, geopolymer concrete with high strength is made from a combination of key components that provide both durability and strength while being environmentally friendly. The primary components are aluminosilicate starch, typically by as metakaolin / silica fume, which provides silica Si and alumina Al for geopolymerization. Fly ash byproduct from coal-fired power plants. Fly ash is rich in silica, SiO2, and alumina, Al2O3, which are key to forming the geopolymer matrix. Fly ash helps create strong and durable concrete when activated by an alkaline solution. Or slag, a byproduct of steel production. Slag contains similar chemical property to fly ash and is often used in combination with it. It contributes to the strength and resistance of the concrete to chemicals and thermal stress. Metakaolin also, a calcium form of kaolin clay. Metakaolin is a highly reactive material that can enhance strength and workability of geopolymer concrete. Or other aluminosilicate, some formulation use natural mineral or waste materials such as rice husk and brick mud, something like that. And then the second is alkali activator. Alkali activator usually a combination sodium hydroxide, NaOH, or potassium hydroxide, KOH, and sodium silicate or potassium silicate solution to activate the blender. Sodium hydroxide and NaOH. A strong alkaline solution, sodium hydroxide, is commonly used to activate the aluminosilicate blender. It dissolves the silica and alumina in the source material to form a geopolymer network. And then the second, sodium silicate, is usually used in the geopolymer concrete also. And Na2SiO3 often combined with sodium hydroxide, sodium silicate, water glass provides additional silicate to the mix, further promoting the formation of the geopolymer network. Fine aggregate. Sand are added fine particles for better texture and strength. Sand. Fine aggregates are added to the geopolymer mix to provide bulk and texture. The choice of sand affects the workability and strength of the concrete. Well-graded sand helps to ensure a uniform distribution of the blender and activators. And after that, coarse aggregates. Gravel or crushed stone. Coarse aggregates are used for structural purposes, providing the necessary strength and reducing the cost of concrete. The size and type of coarse aggregate can influence the concrete's final strength. Usually, you can use the greater size for the coarse aggregate, that is reduce the compressive strength. But if you use the smaller size for the coarse aggregate, that is can make enhance your mechanical performance. And then steel fibers, it could be optional actually, but in the case of SFRGPC or steel fiber reinforced geopolymer concrete, that is important. Fibers like steel, polypropylene, basalt, or glass fibers to enhance tensile strength, ductility, and crack resistance. Steel fiber can be added to geopolymer concrete to enhance its flexural strength, ductility, and toughness. This is particularly useful in high-strength application where added reinforcement is needed to withstand tensile and bending stresses. Water. Water is required to dissolve the alkaline activators and to help with the workability of the mixture. However, the water-to-blender ratio needs to be controlled carefully to avoid weakening the final structure. Also, superplasticizer also, or additives optional. So there is demand on your water usage in your mix design. In summary, the strength of geopolymer concrete is primarily influenced by the choice and combination of aluminosilicate, such like fly ash, like or metacholine, the proper alkaline aggregator, sodium hydroxide and sodium silicate, and the appropriate aggregates. When designed and mixed correctly, these components can produce concrete with impressive strength, durability, and resistance to environmental factors. This one is how the geopolymerization happens inside the concrete, geopolymer concrete. Raw material-based material like slag or metacholine or material rich in silica and alumina, mixed with an alkaline solution such as sodium hydroxide or sodium silica, and that happen dissolution. Dissolution is when the alkaline solution triggers a dissolution reaction in the base materials, breaking down their structure and releasing silica, SiO4, and alumina, AlO4, ions into the solution. Si and Al share oxygen. Silica and alumina ions share oxygen atoms, forming the basic structure of the geopolymer. Oxygen acts as a bridge connecting Si and Al atoms. For monomer formation, the dissolved silica and alumina ions begin to link together, forming monomer units which are small SeO-Al or SeO-Si, Si or Si structure. And then after that, oligomer formation. These monomers then join together into small chains called oligomers, marking the first stage of building a more complex structure. After that, polycondensation. The oligomers start to bond with each other through polycondensation reaction, creating a larger, denser polymer structure. And the lastly is 3D network structure formation. Through continued polycondensation, the polymer structure expands into a strong, three-dimensional 3D network, creating a hard, durable material. This step produces high-strength geopolymer concrete, which is resistant to various environmental conditions, making it more sustainable alternative to traditional concrete. Steel fiber reinforced ultra-high strength geopolymer concrete, or SFR USSGC, or you can say also SFR GTC. Combines geopolymer concrete with steel fibers to create a durable, high-performance material. The geopolymer binder made from industrial byproduct like fly ash or slag activated with alkaline solution provides eco-friendly, ultra-high strength. Adding steel fiber boosts tensile and flexural strength, reduces cracking, and increases resistance to environmental stress. Key benefits: ultra-high strength, stronger than traditional concrete, ideal for heavy load application, enhanced durability, steel fiber bridge cracks, improving resistance to damage and wear. Environmental impact, lower carbon emission compared to Portland cement-based concrete. It can be implication for the infrastructure, ideal for roads, bridges, and tunnels. For the precast elements also, beams and tunnels benefit from its strength and crack resistance, and protective structures as well, suitable for high temperature and corrosive environment. SFR USSGC offers sustainable, long-lasting concrete solution for demanding application. To make geopolymer concrete, this one a process production for general geopolymer concrete. You can see in here, this is a raw material from the fly ash, metacholine, GGVS that will have alumina silica content of each the materials. Sometimes use one of these materials, sometimes combine three of these or more of these, or just two, so it depends on your target for your result, your research. To make geopolymer concrete, start by preparing raw material. Use solid material like fly ash, like metacholine, there are rich silicon alumina. Mix this with an alkaline activator solution. In here, using sodium hydroxide. So this is a form of grain, sodium or potassium hydroxide, silicate or mix of them. This is one sodium silicate in liquid or solution. It's called water glass also. Adjust the concentration and ratio of the alkaline solution based on the desired concrete strength and performance. First, create the alkaline solution, mix together, and then let them in the room temperature because it is hydration inside. So make it the lower temperature, allowing it to release heat in the exothermic reaction. Then add sodium silicate and mix thoroughly to ensure uniformity. Next, pour the solid material into a mixer and slowly add the alkaline solution while stirring. This process initiates the chemical reaction needed to form the geopolymer. Once blended, add fine and coarse aggregate like sand and gravel, and if desired, super plasticizer to enhance workability of steel fibers to increase strength. Pour the well-mixed geopolymer paste into molds, compacting it to remove any air bubbles and ensuring even distribution. Geopolymer concrete usually requires curing at a higher temperature than conventional concrete to accelerate the polycondensation reaction. This can be done in an oven or sunlight, typically at 60 until 80 degrees Celsius for 24 until 48 hours. After curing, remove the hardened concrete from the molds and test for the quality through strength and durability assessment. Following this step will yield high strength, durable, and eco-friendly geopolymer concrete as an alternative to cement-based concrete. The different side for the process production here is this is because we have to add the steel fiber into the production process. At first, procedure began by preparing the alkali activator solution by dissolving anhydrous NA2SiO3 anhydrous water and water gas. That is made to prepare like 1 day before because this is make it at the temperature. After the preparation of dry material, all the material have to oven dry and at 100 degrees Celsius for 24 hours, making it drying, and then sieving the sand. Sieve the sand using 300 micro ms. So all the size of the material, raw material is less than 300 micrometer mass. If your material is bigger than that, you have to grinding and sieving. Something like slag in here. I have a bigger size for slag and random, not uniform the size. So I have to grind the oven dry slag to achieve.
Mrs. Lely, 7 more minutes.
Okay. Make a faster. Then sieve it using 100 micro ms. Weighing and then mixing the dry materials. Then after that, combining activated solution and dry materials. After the all materials is uniformly distributed, and then adding steel fibers, transfer the mixture larger container, add steel fiber, and manually mix until fully integrated. In this picture, I cast the mortar or mixture into the prepared cube mold size 5 times 5 times 5. This is a cube mold, small cubes, compacting it to ensure density. And then we can use vibrator to ensure all the materials is mixed together and testing for the cubes. After 2 days or 48 hours at the room temperature, and then we weighing, remove the concrete from the cube and then weighing before oven curing. After that, we have to oven curing around 90 degrees Celsius for 48 hours. And then weighing more and then let them store the geopolymer concrete in the ambient temperature until the testing days. This one, the comparison of the result of the mechanical strength of the geopolymer concrete. There is compressive, tensile, and flexural strength of geopolymer concrete. I make the comparison in here. I compare to the geopolymer concrete and normal concrete. So compressive strength, average compressive strength is 60 until 70 MPa, higher than normal concrete, average 40 until 45 MPa. As for GPC, yang steel fiber, has the highest compressive strength, reaching up to until 180 MPa, 180 MPa, making it suitable for heavy structural application. And then tensile and flexural strength, GPC, tensile around 5, flexural strength around 9 MPa, good enough without steel fibers. And then with the use of steel fiber, tensile strength reach up to 9.5 MPa and flexural strength up to 18 MPa, showing a big improvement due to steel fiber. Normal concrete also limited tensile and flexural strength, 4 MPa to tensile, 6 MPa for flexural. In summary, SFR GPC perform best due to steel fiber, followed by GPC for its strength and eco-friendly swalency. It's suited for light construction. Okay, this one I want to explain how to factor affecting the mechanical strength of steel fiber. The first is material composition. Material composition, the mixed ratio of main material. It could be have to right composition create stronger bonds and denser concrete. And then silica to alumina ratio, this is important because the ratio it can be determined the polymer network structure. Addition of steel fiber also, the amount on the length steel fiber affect the tensile and the flexural strength. And concentration and type of alkali activator, concentration, a high concentration, especially sodium silicate, strengthen the polymer bonds, but too much can cause shrinkage or cracking. So you have to optimize this mix design. And then curing temperature and time also, it could be a big factor to affecting your mechanical strength because higher curing temperature accelerate reaction and increase release strength, but too high temperature may cause thermal cracking. Control curing is essential. Water to solid ratio, too much water reduce strength, and optimal water ratio improve workability, but without sacrificing strength. And the last is environmental condition during curing. Factor like humidity and temperature during curing also important. Low humidity or extreme temperature change can lead to early shrinkage or cracking. So optimizing this factor is essential for achieving the best mechanical strength in a several GPC, including compressive, tensile, and flexural. Okay, this one is general guidelines for SFR GPC. This is based on the previous study. I make the guidelines for me also for my PhD during research. This one I use how to material composition, how to make the SIL ratio until the environment condition. It is make for me guidelines to help me to how to make the best of the SFR GPC. Okay, the use of steel fiber reinforced geopolymer concrete has some challenge. It could be I have experienced myself how to mixing difficulty. The addition steel fiber makes mix thicker, reducing workability, and mixing and pouring more difficult. So because the steel fiber is making like bouncing your material inside when you casting the geopolymer, and then shrinkage is cracking. As several GPC can shrink and crack if curing is not done properly. So the drilling is very essential for your process production. High cost also, steel fiber increase the cost, making it less economical for large scale application, and lack of design standard because no one standard for the geopolymer concrete is determined how to specific guidelines in a standard more, because this instill reach to how get the all research in worldwide to make a standard or guidelines, and availability of steel fibers
Mrs.
also strict hearing.
Mrs. Lily, time is up. Sorry.
Okay, thank you. Thank you for your attention. And now question and answer. I will give back to host, Ma'am Nurul. Please.
All right, thank you very much. I would like to state some of my notes here. So in answering the high demand for high quality concrete, which is also environmentally responsible. So SFRGPC obviously is the answer. And then Mrs. Lely explains about the SFRGPC, which also answers challenges in modern infrastructures. And then also the challenges that have to face by product, crack concretes, and so on. Now we go to the questions and answer. Anybody?
Ada yang ingin bertanya, Bapak Ibu? Pak Colby, pertanyaan Pak? Pak Rona? Oke. Mungkin dari saya, Bu ya.
Yes.
Oke. Okay, I would like to ask one question. Miss Lely, my name is Irene. I'm a lecturer of civil engineering department. So you mentioned here there are 7 challenges for the use of SFRGPC. And the one is a lack of design standards. So I think this is a very how to say important thing to design some concrete. So how you face these challenges about this lack of design standards on your research? Thank you.
Okay, thank you, Mrs. Iran. Very interesting question. For me, during my PhD, I'm using advanced technology like AI or machine learning for the design optimal geopolymer concrete mixer based on data-driven prediction previous studies. This model analyzes variables like silica alumina ratio, steel fiber content, and water content to generate optimal combination for compressive strength and environmental resilience. So reducing trial time and development costs, because if I using AI machine learning, reduce my work in lab and reduce the cost also. So ya membantu banyak. So have to much using AI or machine learning. I'm using XGB, ENN, artificial neural network, or Jupyter notebook also. So I make the program how to make a mix design optimized to my formula. So this one can reach the compressive strength also my target.
Thank you, Ms. Lely.
Okay, thank you.
Audience, is there any question for our presenter, Mrs. Lely Marini? No? From the online? Right. No? So I can conclude that Ms. Lily, you have a very brilliant explanations here about how we actually must adjust our materials and the futures of building materials. So Ms. Lily, thank you very much. I hope you come back here soon with your new title.
Thank you, ma'am. I sincerely thank you
Ladies and gentlemen who joined this webinar online, could you please open your camera? On your camera, please, because we're going to have a photo taken.
Okay.
Excellent. Thank you very much, ladies and gentlemen. That's all our international webinar for today. And I can tell that from the explanations of our wonderful, great scholars and also researchers, we learned a lot today. And then hopefully we're going to create new collaborations among participants and also presenters. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, guys.
Excellent. Thank you very much, committee. You did very well, all of you, students and Ibu Iren. A very smooth international seminar.
Thank you so much, Mrs. Nurul.
Those with online room, you may leave the room. Thank you very much, all speakers and participants. Thank you very much, all speakers and participants.